This is the agenda for GenoFest, the morning session, up on the slides, and welcome also to those of you on Zoom. I'm going to give a talk, and then we're going to hear from a number of other people in the UMGC. My title has changed. Before it was Technologies and New Service Models, but I realized that it's really more new service models that I'm talking about as I evolve into more and more of an administrator. I more and more talk about organizational structure and money, and that's going to be a lot of what I'm talking about today, but hopefully relevant and interesting for you all. So I'm going to talk a little bit about our org chart and some housekeeping for the event. I've got some good news to report regarding finances, and then 3 topics. A little bit about a new dual tier service model that we're going to announce. A bit about our sequencer suite evolution, which is going to be buttressed by talks from Element and Illumina, and then a little bit about what we plan to do with our CCRB lab. We also encourage you to go and see the lab. So let's first talk about our org chart. This is the UMGC. We're about 40 people. If you look at the people who are directly involved in our service operations, that's about 35. The core people who work in the lab, that's about 30. These are people who are actually processing samples. And then the innovation lab, from whom you'll hear today, is about 5 people. They're doing grant-funded research and are semi-independent, but an integral part of the UMGC. I wanted to call out Dinesha Walek, the managing director. You'll hear from her today. She's taken over in many ways the burden of following up on projects that had been, at least until about a year ago, my primary responsibility. I want to thank our sponsors for them coming. The whole point of GenoFest really is for our vendors to be here and to be able to meet the community. In other words, a genomics focused vendor fair of the type that occur on campus, but specifically for you folks, our clients. I also want to thank participating cores. As you know, in the top left, we've worked with MSI for years, but increasingly we work with the Imaging Center on spatial omics. Now that we're doing Olink proteomics, which you'll hear about today too, there's a way in which we're now working with them, flow cytometry up front of single cell, with Multiomics coming online. All of the cores are kind of blurring in many ways into each other, and that's kind of an interesting evolution we're managing. We're having lab tours today. The lab is down the hall. If you exit from the door over there to the right, please come and visit the lab. You can see technologies. You can see the cool Drosophila or microinjector, robotic microinjector that you'll hear about. You can talk to scientists. You can see the element Aviti and so on. And I want to thank Shay Anderson, our communications lead, who's done not just a huge amount of work for GenoFest today, but has really upped our game as far as communications in general over the last year and a half, 2 years. Okay, so some good news. I have been very transparent in the last couple of years about financial difficulties, and I promise, even though I'm repeating some slides, this is the last time, I hope, that I'll be talking about this. This shows that over a long period of time, as the UMGC grew, it's the kind of like maroon color, our subsidies didn't. And if you look at that in a more granular way, you can see that our financial support over a period of time kept dropping, and it's caused real stress for us. Another thing that happened is we were organizationally moved into the OVPR, and that resulted in a big increase in what we have to pay the university for space and so on. And so really we had a crisis over the last 3 years, which as I'm sure our clients have experienced too. All sorts of things happened. We were a major player in COVID testing and sequencing. We ceased receiving subsidies, partly that was of our own volition. We didn't want to take subsidies that were too low. We ran deficits. We needed rescue. We did get money from COVID, so there were some upsides. And finally, after 3 years, this crisis that was in many ways precipitated by COVID and the funding crisis, the university has dealt with administratively. And that's kind of what I'm happy to talk about. You know, wise people say wise things, and that is true. I'm maybe not as wise, but you know, I thought I'd put myself up there. But I'd like to credit the people who've been responsible for the money that we're getting now. First of all, Shashank Priya arrived a year ago, and he made it his absolute top priority to get money for the UMGC. So you should understand that both Dr. Priya and the OVPR really went to bat for genomics at the university. I also want to thank the Budget 6. These are the people ultimately who hold the purse strings. They agreed, and this includes apparently a very strong level of advocacy from Dean Tolar and others. So the fact that we have money now is, you know, partly because we've been a very squeaky wheel for quite some time, but also the university listened. We also have new support. One of the things that Dr. Priya has done is to brought in an associate VP dedicated to centers and institutes. So we now have somebody who's going to really be our advocate at a pretty high level. And a med school group has been put together to keep us honest, to keep us accountable. And so we like this. I mean, this is a good thing. So, so how to use money? Like, how is it that it's a start? Well, you use it to solve problems. And here's the problems we have. First of all and foremost, turnaround time. No surprise to any of you. And not just communications misspelled, ironic. The communications have to be improved. Our rates need to be more affordable. We need to invest in technology. And we need excellence in the cutting edge of single cell and spatial. So that's a lot of problems. Money doesn't, you can't just pour money on problems. You have to think about how to make those improvements. And so that's what I'm about to discuss now. So this is a model for 2024, this fiscal year, of how we're using the funds. And you can see on the right as the pie chart that part of the money is going to cost reduction. So it's funding things like general infrastructure and instrumentation costs and the cost pools we pay the university. These are going to be covered with those subsidies. And part of it is also going towards technology promotion. So this would be more like promoting the cutting edge of things. And you can see it's about 3/4 into cost reduction and 1/4 into high tech. But as I'll explain, that money into cost reduction also does things like increase turnaround time. So let me talk a little bit about distributed costs. These are these are the costs that are kind of like our indirect rate for things like me and this event and so on. And that percentage is calculated and added to your rates. Like if you buy a flow cell, we have to add that to your flow cell. The new support from the OVPR will dramatically reduce this distributed rate. So for instance, last year you were paying 26.7% on top of whatever direct costs there were. And the external people were paying 32.1%. This year, you're only going to pay 8.6%. So it's going to be a very, very big savings to you in all of the rates. It'll result in about an 18% drop in prices relative to what they would have been if we hadn't had those funds. On instruments too, instrument costs are added only to the services that use them. So we can't charge, some nanostring customer for sequencing. And you can minimize those in two ways, which we've always done. You just don't have a lot of instruments. And you solicit external work to keep those instruments busy, so you distribute the costs more widely. Well, of course, both of those things result in blockages, especially during times like October prior to the November grant, where everybody absolutely needs their data. What you really want to have is more instruments than you typically need to run. So the new UMN support will dramatically reduce these costs. So those, for example, were last year's cost for the NextSeq 2000, and this year it's free. It's been fully paid off. The maintenance costs are fully covered. There are no additional costs. So the NextSeq runs are going to drop really dramatically. So, I love to talk about fast, cheap, good. As you know, good is really not an option. And one of the problems we had in the past is that what we called our standard rates, which were really designed to be cheap rates, to be inexpensive, were really not that cheap. And you compare them to other places, and they were actually already pretty high. And so the new savings tier I'm going to talk about will really actually be cheap. This is an example. I've just taken a whole bunch of rates we've calculated. The blue lines that are indexed to 100 are last year's rates. And as you can see, the new rates, and these are just for the short read sequencing rates, drop from a few percent to kind of about 25%. So this is a really big drop. This gives you just a little bit more examples of the tables there. These are NextSeq runs, for instance, and you can see we were upcharging $1,000 or $1,500 every time you did some of these runs, simply to cover things like rent, heat, light, and so on. And that was not the case at other universities. But a little bit about a standard rate. We've always shot for having affordable rates, and we always called those standard rates. And we've now asked ourselves, well, why are we saying that is standard? And this is where I need to bring up Maslow's hierarchy of needs. As you probably may know, a famous psychologist who said that what people need first are their physiological needs: food, rest, safety and security, love and belonging, and so on. And that what people worry about most are those primary needs. Well, when we think about our clients, we actually do a little bit of puck psychology on them. And what we've always thought is the first thing that they need is to have low-cost services. It's typically what they ask for most. And then, of course, they want fast services. Well, I'm here to say that you can imagine times when the primary need for somebody is, in fact, safety and security, is in fact fast services. There's all sorts of times during the year when people say, I don't care how cheap it is, I need the data now. If I don't get my grant in, I won't have anything. And we've never really served that need. And so I'm going to talk a little bit about how we do that. And of course, our clients also have need for love and belonging, self-esteem, and self-actualization. So How are we going to have faster services? Well, we've always had what we called expedited rates, but they were really punitively expensive and very sparse. We only offered them for a few things, and you couldn't rely on them. Our new speed tier is going to be guaranteed fast and available. So let me talk about that a little bit. These were our old rates. I've just come up with some examples of 2 unnamed services that might have, for instance, a 4 to 6 week turnaround and a 1 to 2 week turnaround. Now we're going to have 4 different tiers. It's confusing, and I'll get into that, but I think it'll be useful. Our standard tier, we're no longer calling standard because that's kind of a judgment we've made on what you find most important. Our new approach is basically just going to be called savings. We're calling it what it is. It's a low cost rate. And the expedited will be called priority. I mean, that's for when your hair is on fire, and it'll still be expensive, but that's the kind of thing where we can get the data back to you in a week. We can always do it. It just becomes quite arbitrarily expensive. What we're adding, though, is this speed tier and a scale tier. The speed tier basically will be fast. It won't be as fast as our really, really torridly fast expedited rates were, but it'll be much quicker and it'll always be available for most rates. Although please note the asterisks in place, which I'll talk about in a moment. And then the scale rate is for very large experiments. Now, if you look at the prices here, what you can see is these prices here, it typically was like 1.5 to 2 times more expensive to do an expedited run. These are our new prices relative to this old standard rate. So you can see that the savings are actually going down. This is despite the fact that there's been about 5 or 10% inflation in reagents. We're actually going to be charging 10 to 15% less. So it's like a 25% reduction in price overall. Speed will be a little bit faster, but because all of our rates are going down, it actually won't be that much more than what you're paying now, except it'll be fast and guaranteed. And then we'll still have priority rates and quite low rates for very large projects. So a little bit about these asterisks. What do I mean by guaranteed or will be charged as savings rate? It is going to be the case that when we take on some speed projects, we miss the turnaround time. And this might be particularly common in the first, quarter or 2 quarters of doing this. What will happen at that point is that we will reflex the price automatically to savings. You won't pay for speed if we don't deliver it. So it's guaranteed in that sense. An important point here is that we're going to start to really track carefully that turnaround time is our turnaround time, not your turnaround time. A lot of the time what happens in projects is we've got the project and then we give it back to a client and they take a week to get back to us. And we can't really move forward until we've gotten information from them. So a project like this is 14 days, not 22 days, because it's just the time that we have control of the project. We have to putting in places ways to be able to track what time is ours and what time is yours. Why are there 4 tiers? The one thing you'll notice with the rates is that these tiers is that a speed tier will be limited in terms of scale. Obviously, if we're going to promise to do something in 2 to 4 weeks, it has to be a project of a size that can fit on the sequencers. If it's more samples that can physically be run in that period of time, obviously we can't do that. And so we have these 4 tiers because sometimes even savings, has a limit for the turnaround time. So really, the 2 reasons here is that having all these tiers allows us to really prioritize small projects such as this, where we might have very, very strong constraints on you, like you must run 10 samples and only 12 samples and only 12 samples. And sometimes we need to account for projects that are too big to guarantee any TAT at all. That often happens. Okay, the speed tier will always be available. There's an asterisk there, and what do I mean? It'll be mostly available. And this is a wordy slide, but I really do need to read through it. The NIH and the university don't allow us to charge unjustified core facility fees. We have to say what it is we're charging you for each time. We can't charge one PI to pay another. We can't arbitrarily prioritize one PI over another in terms of speed. So we can't just say, hey, your experiment, your turnaround time is faster because we charge you more. We have to say we charge you more because we use these different people and these different instruments and these different reagents. So we can only offer a fast tier when an instrument is not limiting, where we've got enough instruments, for instance, on the MySeqs and so on. If an instrument is limiting, we can only achieve a speed tier if we've got multiple instruments, or we can model what it'll cost to buy another instrument, or we can otherwise accelerate TAT, like we can run a flow cell 3/4 full. Those all make it more expensive, but we can offer that. So I'm just saying that we'll never have more than one NovaSeq 6000. So we won't have speed tiers on that instrument. It's just not possible for us to do it. We'd have to break rules. Okay, just as important as turnaround time is communicating turnaround time. What we often hear is we wouldn't mind if it took so long if only we knew, and we get that, that's very true. This is a dashboard from last night of the projects that we see. All you really need to notice is that there's lots of red numbers and that those red numbers are each a project, each of which might be a pretty big project. And so it's really quite a challenge. Nevertheless, that's something that we need to do. And so each of these tiers is going to be associated with a different degree of communication, where priority projects, you're going to get an email or a call daily. Speed, anytime we do something to the project, you'll hear from us. And then the savings and scales tiers, if we hit a major milestone, and Dinesha is going to talk more about this. How will these services work? Well, once implemented, we're going to list all of these tiers on our website. Our quotes will automatically always include all of the service tier options. So when you get a quote, we'll say, these are the turnaround times in quotes. You won't have to ask for an expedited or a priority or a speed or a savings quote. They'll always be offered to you. And here's an example of one of these in development. This is a MySeq run processing rate, for instance, just for the work that we do in the lab. And if you look at the left hand there, that's this year's rate, and last year's rate was 389. So you can see that compared to the standard rate, it's now actually less expensive, whereas the new quick tier, which will be a faster turnaround time, it's just marginally more expensive. So you're going to be seeing this across a lot of our services. The bigger question is not how will the services work, but how well will these work? We're asking for forbearance for the following reasons. It's going to take a while. We are over hiring now in the first time in our history. So we've decided to hire 4 or 5 people to simply provide excess staff to deal with people who might say, yes, we really do want this in 2 weeks. We're going to finish consolidating our operations offsite. That's critical for speed by year end. And if the speed tiers are very popular and everybody says, you know, we're actually willing to pay that because we've modeled out what it costs, we're going to have to buy new instruments. We'd buy another NextSeq, we'd buy another Aviti. And then of course it would take, a couple of months for the instrument to get in place and installed and so on. So a little bit about the space then. Savings and speed are about more than money. And this is a picture of what we looked like back in 2019. And it wasn't efficient. We were spread out over a lot of labs. And as we grew, those labs became increasingly crowded. This worked originally having these separate different places because we had services broken up in a way that kind of, CCRB would do one service, Snyder would do another. But then as we grew and became more and more of a sequencing shop where we were doing next-gen sequencing, that came to the point where it was actually taking up almost all of our work. And that wasn't something we could easily split between groups. And it started to become increasingly inefficient to work that way. So what our map is now is we've been out in Forefront off campus, and we moved there because of COVID. The site has got the kind of space that you really need for an industrial scale genomics core, a huge amount of space. And we've been there for a while, but here's what's going to happen. In January, we're moving within Forefront, which is in Oakdale, and to a much nicer space. It's about the same size, but much better for genomics. And all the folks from Snyder are going to move over there this quarter. So by January, all of the wet lab processing that we do for all your projects is going to be done 10 miles from here. The innovation lab, which is currently taking up a good amount of our CCRB space, will take over the Snyder space because people will have moved out, and this will become a place for single cell and spatial. So let me talk briefly about sequencer evolution. This was from GenoFest a year ago. We talked about how we mostly were in Illumina shop, and there was this NovaSeq X Plus. And the question was, do we upgrade? I can tell you this much. We've been using the NovaSeq X at a partner. It's awesome, and we're not getting one. And what I mean by that is, and I don't want to, I went over this in June, so I'll just fly through it now. But the reason we're not going to is because if you look at the actual runs we've done, and you compare how much this would be on the incredibly high capacity NovaSeq X Plus, what you see is that you end up having a lot of extra charges that we'd have to add because we wouldn't be running it very frequently. And our cadence for runs would be like 3 weeks. So nobody wants to have, the benefit, the reward for us buying the instrument would be that it would be more expensive and slower than to outsource. And so instead, and we have this problem that we'd be neither cheap nor fast. It would be good because it's an incredible sequencer, but everybody would be upset. So we're not going to buy it. And the questions are, but what if there's a huge increase in demand for the sequencer and all of a sudden you have enough volume to run it? Well, let's hope so. And if so, then we could buy one. Don't we have funds to buy it? I mean, I was talking about how we brought in new funds. We do, but they're not unlimited. That NovaSeq X Plus would consume all of our instrument budget for the next 7 years, meaning we wouldn't have funds to buy anything else. And there's lots of other things that are important. The biggest question is, but don't we need access to it? And absolutely, you need access to it. And we're going to make sure you do. And here's how we're doing it. The theory, and we talked about this in June, was that a lot of cores are going to have this instrument, and they're not different from us. They'll have exactly the same problem that we would have if we bought it, and they'll be hungry for our libraries. And so we may actually do better by sending our stuff to them by buying it ourselves. And it's a win-win. I mean, this would be great for them too. And so the challenge for us would be to make this a virtual instrument. And Aaron's going to talk about how that'll be the case. Well, I'm happy to say that since then, we are working with those 3 cores, which is Chicago, Madison, and Illinois. And we've gotten what they'll charge for us. And we've talked about terms. And those plots on the right show that these prices here, we would call we're calling it a Midwest blend. It would basically, the prices modeled using for our slower tier, we'd always send it to the place that might take longer to run it because they've actually got a lower price. Whereas for the more expensive tier, what we call our speed, we'll send it to a place that's got 2 of them. They charge more, but they say they can run it the next day or the day after that because they've got a really big output. So I put a dashed line here because, of course, there are many other places that'll have NovaSeq, some of them commercial, and we really think that that's going to actually be how we'll deal with Illumina. Nanopore was another instrument we talked about. We've decided that it's a little too democratized for a core. And PacBio, I mean, it's a great platform. It's just not something where we have much to offer. PacBio, let's talk about that. As I said in June, this is an upgrade that we thought we would do. We really need it, but it's turned out that partnering is going to work for that too. The reality is that we're currently outsourcing PacBio runs on our Sequel II when we have overflow to Mayo. It works well. That outsourcing is actually less expensive than it costs us to run our own. And the higher capacity of the Revio instrument, which is great, is going to cause the same problems NovaSeq X Plus was. So again, we're going to continue to promote PacBio Tech, library creation, QC. We'll just ship the libraries there and sequence them there. Okay, these were the other platforms we talked about last year. We've made the following decisions for now, that these platforms that we assessed internally were not interesting enough to warrant the cost and effort to change track. And the ultimate genomics instrument, this is kind of revolutionary, very out of the box, but it's really much too expensive and not mature. That would be too risky for us. We've plumped on getting the Element, and I'm not going to talk about it now because we've got Element here today, but the main points are that it's different enough and practical enough to work. We actually have it. We've been running it. You'll hear about that both from us and from Element. Lastly, third topic. Want to talk a little bit about what we're going to do over in the single cell. So this is really about technology promotion. This is the other way we're using our funds. We're now going to make a couple of our highly trained, dedicated staff who work on single cell genomics and spatialomics free. When I say free, I mean free for all PIs. And right now we're saying that'll be 20 hours of free effort for them per year. Above that, you'll be charged. If it turns out that there's less uptake, maybe that'll increase to 40 over time. The other problem is if you think about NextGen as a common engine for a lot of different workflows, if you look at the input to those workflows, it's always been dead material, DNA, RNA, straightforward stuff. You can freeze it, you can store it, you can transport it, you can ship it. That is not true for spatialomics and single cell. These are both workflows that themselves have an engine. It might be the Chromium box, it might be the GeoMix. And getting material into those boxes is really difficult because a lot of the time it's living material, or it's precious material, or it's material whose quality, if it's poor, completely destroys the data at the end, kind of garbage in, garbage out. And up until now, we said, well, that's kind of your problem. That doesn't work. Nobody wants to hear that. We have to make it our problem, and we need to provide solutions for it. And so that's what we're going to be doing in CCRB. We'll have a lot of space. If you go down there and look at it, you'll hear from Pat and Fernanda how we'll use it. Ultimately, those funds are going to do things like buy this instrument. You'll hear about this in the next month via emails. It's called the Tapestry. It's a targeted single cell amplification device. Unlike the devices that you're currently familiar with, like the 10x Chromium, this is used for assessing targeted DNA mutations in cells. So really useful for like clonal evolution, leukemias. It can be used for genome editing work. It's an expensive platform. We're making an investment. We've reserved money by not buying those large sequencers to allow you users to try this out. That's the idea. And we hope to have many more such boxes. If you think about the kinds of things you might need, maybe we need to put tissue culture hoods in place so that you can come and do tissue culture work. Maybe we need more computers so that your lab staff can come and work at a workstation. Perhaps we need cell isolation devices, tissue dissociators, more, we've purchased part of a flow cytometer that's specifically dedicated to single cell use. Maybe we need more 10x Chromium boxes so you can come and do the work yourself on weekends and nights. That's where we want to make an investment, not in what is ultimately a commoditized sequencer. Ultimately, this is what we want CCRB to be. It's quite a change. We're going to open up the doors, invite you in, and hopefully have it to be this place where you can come and use instrumentation, get training with a happy staff. There is, however, a problem with that metaphor, because if that's the magical kingdom, then that's me. And I'm okay with that.
Okay, thanks, Kenny. Appreciate that. I'll be talking a little bit today about single cell and spatial at the Genomics Center. Really happy to have the invite here to speak again at another GenoFest for such a great crowd. I see a number of people that we've worked with pretty directly, and vendors we've got so much great support from. So just going to talk through a few elements of what's happening in single cell and spatial. I'm the lead for single cell, as Kenny mentioned, and Fernanda will be coming up in a few minutes. She leads all of the spatial projects within the Genomics Center. I've got a short talk today, so I'll talk a little bit about what I'm not going to talk about. In the past on this stage, I've talked a little bit about kind of chemistries for single cell transcriptomics, including what's pictured here is 10x's microfluidic chemistry. I don't quite have the scope to talk about that today. There's a lot of really great resources for introduction to single cell. If you're interested in that, I'm happy to connect you with those. I've also kind of in past presentations here talked a little bit about what our process is in terms of a workflow for taking in projects, how we go through the stages of project design, library prep, through sequencing, and ultimately delivery of a data set. And I think that's pretty relevant to this audience, but I'm not going to focus too much on that here today, other than to talk a little bit about the consultation stage. A few of the topics I'll try and touch on here. We'll also include talking a little bit about DIY, and Fernanda's going to present that portion of this presentation. I'll talk a little bit about some recent projects in single cell, as well as talk about some emerging technologies that might be exciting or interesting to you all. So let's talk first about kind of the consultation stage of projects. As Kenny mentioned, we are now offering 20 hours a year per lab for project consultation, and that includes meeting with us, talking about your project. It can include training. It can include kind of going in and doing background research, or working with people in your lab to get them up to speed so they're comfortable using some of the instrumentation that we'll make available. And I think that'll be a nice feature to have available to many folks here. In terms of these, in terms of what we like to talk about in consultation, we're often working with pretty early stage projects. Sometimes labs will come in with a lot of deep background in single cell and a really specific idea of what they want to implement. Other times, things are at an early stage, and we're happy to take in projects at really any stage. We can provide support for grant applications. We can't necessarily write your grant application, but we can certainly help lay out what the experiment might look like and what to expect at maybe different stages of the experiment. We can offer a letter of support and estimated quotes for that work as well. Some of the things we often like to talk about are, you'll see throughout today many of these different technologies and boxes. what technology should we use, where should we start, what to expect, how do we address those types of questions. We're really interested in talking about your model system and biological questions. Fernanda and I both have backgrounds in academic research, and we really take pains to make sure that we're matching all of the available technologies and approaches that exist within the Genomics Center to your model system and biological questions. We talk a lot about longitudinal studies, including fixation and targeted probe-based approaches, such as 10x's RNA flex chemistry. We can talk about pricing and capture scheduling as well, and the kind of technical elements of projects, from talking through tissue dissociation and cell preparation, details of sequencing. How should we sequence this? How should we pool? How many reads should we shoot for? We can talk about long read approaches and things like cell surface proteins for people who are interested in using oligoconjugated antibodies to add that into their single cell workflows as well. I'm going to skip talking about example data for now. However, I'll talk a little bit about some recent projects. We've been, one thing that we've implemented recently is some developments to our kind of shallow depth QC for single cell projects. We've transitioned from universally using a MySeq-based QC for each project to a more custom structured NextSeq QC, in which we basically target each project based on its parameters to produce a data set that's going to be more predictive of the final data set. This is something that we offer before you go in and take those steps of sequencing on a NovaSeq, for example, just to get an initial look at the data set and make sure it's going to meet your needs. One element of this is we've seen that multiplexing is a really significant cost reduction factor in experiments, but we've also seen that it tends to be sensitive to titration of antibodies used for multiplexing and to how the samples are washed and prepared. We've begun to offer this multiplexing QC at this stage as well, so we can kind of give you an idea of how well those multiplexing steps worked in your experiment. We started to put some single cell projects on the Aviti element sequencer. My colleague John will talk about that shortly, and we're excited to begin using that sequencer for these applications. We've also recently gained access to the Miltenyi Tito sorter. This is it's a cartridge-based flow cytometry approach that we've been applying for a number of single cell projects. We're happy to get you training and access to this instrument. One application that we've used or kind of developed for use so far is using the Tito for purification of nuclei. This has applications for single nuclei ATAC-seq and single nuclei RNA sequencing as well. We've made efforts to work more closely with the excellent team over at MSI-RIS and to really include their team earlier in the projects. Kind of an application of this is if you're looking at something that's more towards an advanced application of single cells, such as looking at developmental trajectories or pseudotime analysis, we really try and make sure initially that the data set we're ultimately going to be producing is going to be biostatistically and quantitatively appropriate for some of those types of analyses. And we work with labs on custom applications as well, that someone may come in and say, this is something that we would like to do. Can we work with you on doing this? ASAP-seq refers to a multiplexed ATAC-seq single nuclei tagging, and we've also done some work on custom readouts for insertion mutagenesis projects. That leads a bit into some emerging technologies in the field, many of which we've already started kind of dipping our toes into. The area of cell purification and isolation continues to develop. There's been now commercialization of technologies for putting cells into a paramagnetic field and using those to separate out viable from non-viable cells, which has advantages for processing these types of projects, which are very sensitive to any kind of dead or dying cells in the media. We have started working with Parse on MassSeq technology. This is multiplexed array sequencing, and this is a long read approach using PacBio sequencers. If you're interested in taking a single cell project to the level of looking at exon splicing and inclusion, broader elements of RNA structure than could be detected with a short read Illumina sequencer. MassSeq is a pretty powerful technology in that area. We're also excited to be working with parse genomics. This is a combinatorial barcoding based strategy for single cell. It has advantages for large and highly multiplexed experiments. It's a fixation-based approach, and it also has advantages for situations where the cell size or the cell morphology might make it less appropriate for a microfluidic-based separation. Furthermore, and finally for my section of the slides, the field of single-cell epigenomics continues to develop and iterate. Single-cell methylation sequencing is now becoming available for the first time. And we're also frequently offering multiomics at a single cell level, that specifically being RNA-seq combined with ATAC-seq. So if you're interested in kind of chromatin structure, transcriptionally poised regions, or even getting a more precise kind of plotting of different cell types in your population, multiomics is a type of technology that can be applied in those applications. And with that, I'll move things over to my colleague Fernanda, who will talk a little bit about spatialomics at UMGC.
Hi all, isn't it great to follow great speakers? It's great. So yeah, I have a mask and I have an accent, so hold on to your seats there. So last year actually, GenoFest, I presented about the spatialomics workflows, and I went into details and talked about what to expect from our meetings and what to expect and what the methodologies were about. So I'm not going to do this year. It's out there. There's a lot of resources. I'm going to focus more on what we have for you, we have coming, and what the DIY experience might be, or what we dream about, right? So just we started with the spatialomics about 3 years ago. And at first in our consultation meetings, it was Colleen with the histology group, imaging with Grant, and myself. John is releasing the data to you guys at the end, but and a lot has changed since then. But at the time, until very recently, actually, what we were offering is the genomics full service, okay, beginning to end, and partial service for the 10x genomics Visium. And there was no option. You had to do your own part upstream to the protocol. And I received the libraries, the cDNA, and I made the libraries myself. So that's it. There was no flexibility. Well, things have changed since then. You can see Grant now has been promoted to assistant director of the imaging center, market centers. And not only that, in the last few months, Aaron and Anna have joined the group, and that has been great. So now there are more faces. When you have consultation groups, there's more people there. Don't get scared. We also have been inviting, Christy and her team. Sometimes it's Christy. She's the co-director of research informatics. It's great to have them on board because you guys have statistical questions, power, of experiment and stuff like that. So instead of just setting up your experiment, getting your data, and then going to them and saying, "Can you please make sense of this?" They are involved in the beginning of that experimental design, and that's very important. So we're happy to have everybody's on board to help you and to come up with the best experimental design to answer your questions. So now that Aaron and Anna have joined, what has changed so far? So Aaron took over the genomics workflow. It is full service, and Anna has been just trained on the Visium site assist, and I'll touch on that a little bit later. She's now going to be, so we're now going to be offering full service, beginning to end, like with the genomics. So you give your blocks, you can start with Colleen, and she'll cut, and we'll give you the data at the end. Now, there's also going to be the option of full DIY, except you're not going to touch the site assist. Just that, so Laura has, so the site assist is from Laura Niederhofer's lab, and she very kindly allowed the imaging center to operate it for you guys. So that portion you're going to have, support from them. And I wanted to know that the genomics is also from Laura Niederhofer's lab, so we have a lot to thank her. The nice thing about the site assist, before I move on to the cosmics, is that we're very excited and waiting for the next kit that's going to come from 10x that we hear maybe, possibly, hopefully this time it's true because it's going to be a real game changer. It's the HD, the high definition kit. It's going to be available for human and mouse samples, and it's going to be a 2-micron resolution. It's really a game changer, and it's going to be really nice to see what you guys can do with it. And on that vein, Laura Niederhofer's lab again purchased a Cosmics that is going to be arriving at the imaging center next week, Brent? It's here, guys, it's here, and they're going to be trained next week then? Or they all did it in 2 weeks? Soonish, there you go. So this is going to become a service very soon. So there's a lot of things changing. We're trying to bring more options and get more flexibility, as you're going to see. Options and flexibility. Who doesn't want that, right? So the thing is, right now there is DIY. There's a DIY bench, and some of you have used it. It's nice. I mean, people have all the reagents they need to do the single cell. We have trained a couple of groups, right, that come, at their own time. They have access to the lab and they do their captures, And then we had everybody that has to do their Visium have the option to come and use the DIY bench if they choose so, okay? But we're there to dream bigger, right? As Kenny pointed out, we have a lot of changes coming down the stream, and there are a lot of opportunities, and we invite you to dream with us what it can become. We welcome feedback, we need that, okay? And we have the most important instrument that has been used for 4 years now flawlessly, and we're invited to use it. And it's our Mocha Master. It does make a mean coffee. So jokes aside, one thing that is new on all of this, besides having the bench and maybe it's going to expand and you're going to be able to not have to overlap single cell with spatial, right? Oh, there you go, Pat, you're here, I forgot. So instead of overlapping, instead of making more space, we also do want, and that's Kenny's vision, okay? It's have you guys come over and prepare your samples, in the lab. And that's more to do with single cell, okay? So having a tissue dissociation instrument, centrifuges, your pipettes, tips, everything you need, like basic buffers, we're not gonna have all kinds of, but maybe having catalogs that you can look through and see, hey, this one, I don't know if I want that, but resources. We wanna give you resources and make this a useful place for you guys, okay? And freezers, and Pat now. So the idea is to pack, is to have kits. And that's Candy's idea too. And the bag was his idea. Kits, as you sign up for a workflow, there's gonna be packs, everything prepackaged. So you know the cost, you know where it is. You're gonna be trained. You're not gonna walk into our lab and have to figure out everything. So everybody that's trained has access, gonna have your badge. You're gonna know where to get your packet, where to phone, where to store. And I hope that works again. Also, there are long hours. We don't want you guys coming in and out and having to find a place here at the cafeteria to land, So touchdown spots, that's a premium one. We have a couple in the office. There's gonna be more in the lab. So, you can bring your computer. I heard Kenny said have computers for you guys too, but we'll see. All right, okay. And don't forget the coffee. Anyway, so we already started training. Pat has already trained several folks on the title, giving them access, single cell capture, Visium, but now the next step is doing the full training for folks that want to use the site assist workflow with the imaging center, the genomics center included. Then we're gonna have the original workflow, the Visium, for fresh frozen samples that are not human and mouse, because unfortunately that one, doesn't use probes, but at least gives us access to everybody that have non-human and mouse samples. So that's still gonna be DIY, at least for now. 20 hours, what is gonna include? I'm gonna tell you that with Spatialomics normally, it can get to at least one project, if not two, fully done from beginning to end if I'm not doing the DIY. But that's gonna include training. If you wanna be able to do that in the future, it's gonna include my, the training hours. I'm not gonna write a 5-minute email and count that down. That's not it, or 15-minute stuff. It's stuff that takes more than 30 minutes or 1 hour, right? So the thing that we also is gonna be refreshed every fiscal year. So let's say you use your 20 hours, there's a reduced rate, which is nice. So if you need extra hours, the rate is reduced for those extra hours. And then at the beginning of the next fiscal year, you get 20 more hours, possibly 30, 40, depending on how the use is, the distribution, we will adjust. But basically we're here, what we wanna say is that we're here for you. We wanna hear back. We wanna make the place more useful. So It's going to be slow beginning. We're going to have to move everybody around, but it's really, it's about you guys and working together with this. So if you have any questions, please feel free to reach us. I don't know. Thank you, guys.
My name is Dinesha Walek, Managing Director of University of Minnesota Genomics Center. And today we're going to talk about NGS service updates and Aviti data review. Today's, I will speak first. We're going to tag team with Erin Becker, Instrument Service Manager, and John Garbe, who is our informatics lead. In my topic, I'm going to kind of expand a little bit about UMG org chart and my role, new role, and then expand a little bit more about the service tiers that Kenny talked about, and then some expected FAQs, mainly Aviti related, that we've already handled with clients. So within the last few years, this is the org chart with service oriented. What you saw with Kenny was the previous one with all our staff. Few years, if you have noticed, as Kenny said, we've grown. When Kenny first came about 15 years ago, we were only 9 staff members with limited services, and today we are quadrupled in size and added multiple services. I have been at the university for over 30 years, aged myself. In all its places, I've been part of the core facility, starting with the microchemical facility at the Institute of Human Genetics, and today under OVPR at the UMGC. As with this growth, Kenny could not be involved in day-to-day operations in every part of the project, and that was quite impossible to do. And therefore, about a year ago, we came up with this new role, the managing director, which I've stepped into. With the expansion of services, each service is managed by a service manager. And currently we have over 12 service managers who report to an operations manager. I would like to introduce today our operations managers, Corbin Dirks and Jerry Daniel, and Elise Trolling. All of you kind of have dealt with Elise at some point if you've done an NGS project. She's on maternity leave, and she'll be here with us very soon, next week. Oh, no, the week after, sorry. All right, all operations managers report directly to me by default. Then I'm responsible for all operational staff members. I also am the OVPR HR liaison to the UMGC. Kenny and you guys can sit down. Thank you very much. Kenny and the operations team have worked in the last year putting together managing tools to help us manage better, including staff effort within each project, as well as working with managing tools to help to determine profit loss within each project. We are almost there. We are getting there. In addition to that, one of the other key responsibilities I have that might interest all of you mainly is that I'm the final authority on the resolution of most escalated UMGC client issues. So if you have any issues, you should email me, walek001@umn.edu, and if I can find a resolution, get back to you, and then if I can't do that, I will escalate it to Kenny. But this is the whole goal is to reduce his time so he has more time to work with the higher level administrative work. Service tiers. Kenny rolled out the new service tiers. I know it's getting used to it, these words: priority, speed, savings, and scale. I'm going to kind of show you what it means to you as a client if you did a priority project. You would be handled by one person, and it'll be an operations manager, and they will email you every day. It's going to be a short period of time, so therefore you will get an email whether something happens or not. If you had a speed tier project, you will still get emails from a service manager every time when we touch your project, whether it's internally or whether we send you data and report, let's say QC completed, and then you get back to us. The savings tier, communication is less frequent. We only communicate to send you data or we need input from you. So same thing, a service manager will send you a QC report if you have marginal samples, We want you to let us know whether you want to move forward or not. So the scale, the next scale is scale, and the scale is similar to savings tier. However, it is less frequent communication because they're large batches, so as needed only. We are going to roll this out in the next 3 months. We will ask you to be patient with us so that we can iron out the kinks with our database and putting things together. Hopefully in about 3 months, we'll be operating pretty smoothly. FAQs. A lot of people have asked, hey, with your Aviti system, can I submit my own libraries like we do now? Absolutely. Aviti has on their website that they have over 65 different third-party kits that you can use. The only difference is you do have to circularize those linear libraries. We already have put in place a service to do that, but you can also do it in your own lab and submit, and it'll be seamless to you. We would QC your samples and process them like we do now. Have you tested the Aviti? Yes, we have. We have used 4 of our previous libraries for different types: 10x single cell, 3' GEX, Illumina Nextera XT metagenomics library, Takara stranded total RNA-seq, and Illumina TrueSeq DNA amplicon library. How is the data? Well, Erin's going to talk about some QC metrics for those, as well as John will talk more detail in some of the data review of those concepts. So with that, I'm going to hand over my talk to Erin. Thank you.
Thank you, Dinesha. Thank you, everyone, for coming. So I am Erin Becker. So I am the instrumentation lead for NGS here at the UMGC. And I'm going to be talking about a few different things. We're going to be talking about our NovaSeq X Plus services, the element Aviti, which was installed again late June, so we've had a chance to put it through some paces. A little preliminary review of some of the Aviti run QC data. A little bit on pricing between Aviti and some comparable Illumina platforms, and then just a quick look at the PacBio Revio. So NovaSeq X Plus. So as was mentioned earlier, I'm going to say it here that as the instrumentation guy, I'm kind of disappointed I don't get to have a chance to play with the big instruments. So that is what I'll say here. And I know, and I don't blame anyone, and I hope we eventually get one so I can get my chance to put it through its paces. So we'll still have access to a lot of fun stuff here. So this is the next evolution of the well-known Illumina technology, and we want to make sure that we ensure access to this low-cost Illumina sequencing for everyone here at the University of Minnesota. We have run a pilot project. Data was returned to us seamlessly, and so that went quite well. So we expect this process to be quite seamless. We expect that we will be able to meet current turnaround times. And lastly, the UMGC is going to be managing projects. So much like we do currently for all of your projects, we are going to manage projects in a similar fashion. So this is a current workflow for the NovaSeq 6000. So pretty common here, we get sample QC, we run library preparation, and then of course we're doing this important step of pool QC before we go on to the large scale sequencer to make sure that we're making, that those libraries are balanced and that we make efficient use of the sequencer. Then we create FASTQ files, and we're doing data QC at MSI and using MSI resources for distribution, hopefully making happy scientists at the end. So you're going to see really big changes with the NovaSeq X Plus here in this workflow. So I want to make sure that we look at this carefully. So we're going to add a plane in and a new box maybe. So this is what you're going to see as a user, right? You're really going to see very little change in how your project is managed by us. We're still going to use MSI for all of our data distribution and our QC work, and we will continue to have happy scientists, we hope. And if you've been sequencing with us for a while, you've probably seen Sequencer Home Queues. This is our shared resource for managing projects and sharing status of projects for NGS. And we'll be managing the X Plus in a similar fashion. We currently have the NovaSeq 6000 on Sequencer Home Queue, and we're now incorporating the NovaSeq X Plus as well. So if you're accustomed to seeing the dashboard view, which is more of a high-level summary rather than the actual sequencing queues, the X Plus queues will exist there as well. So again, highlighting here that there's going to be really no change for you as a user, even though we're going to have new instruments and be shipping out to other institutions. And then just quickly, on the NovaSeq X Plus output, 10B single, the 10B cell is approximately equivalent to our current NovaSeq 6000 S4. So, we expect that we're going to be using this one quite a bit for most of our projects. The Q4 release of the 25B flow cell is a very high output flow cell with about a terabase of data coming per lane. So it could be applicable for very large whole genome projects or other very large high throughput projects. So this is my new toy. So this is what I get to play with now. So I'm happy to have that. So the Element Aviti was installed, as I said, late June 2023. Our newest short read sequencer. It is focused more on the mid throughput, low cost mid throughput, 250 to a billion reads per flow cell. And it utilizes these widely available commercial library kits. So we can convert basically anything that you're already accustomed to using and making on your, making for Illumina sequencers, you can also make them compatible with the Aviti. And lastly, flexible run configurations on this instrument. So we're accustomed to these sort of read lengths, 2x150, 2x75. What's important here is that you have different scales on the Aviti. So you have high, medium, and low, ranging from a billion reads per flow cell for the high to 250 million reads for the low. So good for small projects, small RNA-seq projects. And then the high could actually even be used for whole genome projects, smaller whole genome projects. And we can scale this instrument if needed. So the 2x300 base pair also, I wanted to highlight that that's coming soon, so should enable some metagenomic or microbiome projects as well. Lastly, just a quick comparison here, Aviti versus some Illumina platforms. So I'm comparing the 1 billion read output level here between the Aviti High, NovaSeq 2K-P3 flow cell and the NovaSeq S1 2x150 flow cell. So these are based on the savings rates that were discussed earlier, equivalent to our standard rates. Billion reads is sort of that Goldilocks zone for a lot of projects in terms of output. And so the cost per million reads on the Aviti at this level is $2.36. So it's quite inexpensive. And we're excited to see that. We'd like to see our users take advantage of that cost savings. And then the average cost over a lot of these, over all of these runs, is approximately 40 to 65% less for the Aviti. So yeah, you can see that that could be significant for us over time, and for you as a researcher as well, using to spend your research dollars wisely. And then quickly, some quality examples. So as Dinesha mentioned, we ran 4 different library types, the RNA, metagenomics, single cell, and our TruSeq Amplicon. We actually had a 5th run using FIAX control just to benchmark that instrument and make sure we were able to operate it successfully. But what I wanted to highlight is the quality scores that we were able to get. So Q30 here, Q30 a 1 in 1,000 chance that your base call is incorrect. We were getting between 93 to 97% of base calls at this quality level across all these runs. And then also we decided to start summarizing Q40 as well for these internally. And what we're finding is that 81 to 89% of our quality scores are at the Q40 level. So what I did want to point out that while the outputs may be variable, as you see in that column for reads, read quality is extremely high across all of these library types. So I was happy to see that. What we have to do is do a little optimization in the lab to make sure that we're understanding how to load this instrument well. So that's my job. Then quickly, the PacBio. We're not going to be getting this one either, unfortunately, but that's okay. We're continuing our partnership with the Mayo, as Kenny mentioned. We'll continue to offer this as an option for high throughput sequencing on high throughput long read sequencing, getting 3 times more data than our current Sequel II. Mayo has 2 instruments, so we don't expect that we're going to have any problem getting on their sequencing queues if necessary. And as you can see, the UMGC will continue to manage projects in the same way. And we might just add a truck this time, and then the new box. But the take-home message is your workflows will look very similar, if not the same. All right, I'd like to bring up John, who's going to talk a little bit more about the Aviti data.
Thanks, Aaron. I'm going to give you guys a quick peek at the Aviti data that we've generated so far. Element is going to present later this morning and give a more depth overview of the instrument, how it works, what it is. We're going to jump ahead and take a look at what the data actually looks like in our hands. One of the notable characteristics of the Aviti is the very low error rate and base calling that the instrument makes. Here we have a plot. Let's see here. Work on my animations. This plot here is showing the FASTQ quality scores on the y-axis across the 150 base pair read lengths. And this plot shows these 4 different types of Illumina libraries that we've sequenced on Illumina instruments, and then we sequenced them again on the Aviti instrument. And you can see the Aviti data here has a notably higher Q score across the length of the reads compared to the Illumina runs. Here, the first plot is the forward reads, the second plot showing the reverse reads. So the difference in quality here equates to approximately, with the Illumina data, you would expect to see 1 base calling error every 10 reads, and on the Aviti, 1 base call error every 1,000 reads or so. So the Illumina already a very low error rate, and the Aviti instrument even lower than that. One notable item on here, you can see this one particular library type. This is an amplicon data set where the quality drops off at the end of the Illumina data set. This is a very short library, so these are amplicon fragments that are 100 base pairs or so. And on the Illumina instruments, when you sequence through your library fragment, then you sequence some adapter sequences, and then you, if your read lengths are long enough, then you run into the flow cell and you generate kind of some random low quality noise, perfectly expected when you're sequencing short fragments. On the Aviti, it generates high quality noise instead of low quality noise, so you won't see that drop in quality when you're sequencing past the lengths of your fragments. Looking closer at a couple of these different library types, here's a very brief comparison of how a 10x single cell data set looks like on here on NextSeq data on the left side and Aviti data on the right side. For the sample, we have comparable read depths on the 2 instruments, and we get pretty comparable numbers of genes detected, number of cells detected. Our barcode rank plots are basically identical. The t-SNE projections of the data sets are basically identical. So, you know, in the 10x application, the NextSeq and Aviti are both giving highly similar results. Another application example we'll take a look at here is an off-target gene editing detection project we're working on with the Moriarty and Weber labs. In this project, sample of cells are edited with a precision gene editor. The collection of edited cells are then, we extract DNA, sequence that DNA, and then look very closely at potential off-target editing sites to look for small fractions of cells in that population which may have an altered base. And so here's what that data looks like when sequenced on the Illumina instrument. This is a 30 base pair region where we think there may be off-target editing happening, and we're seeing some variants in the data set that are present in 1% or 0.1% of the reads in the library. This same library sequenced again on the Aviti gives us basically the identical results as what we're seeing on the Illumina instrument, which is great. Looking at it another way, with each point here being one of these low frequency variants, we plot the frequency that we get from the Illumina data on the x-axis, and from the Aviti data on the y-axis, we get this nice line showing you get equivalent results between the 2 instruments. It's only when we look at these super low frequency variants that are 1 in 1,000 reads or 1 in 10,000 reads that we start to see the higher error rate in the Illumina data set as compared to the VD data set. So you really have to look super close to in this type of data set to see the presence and the differences in error rates. So I'm going to say that in most cases, the differences in error rates between these two instruments is not going to be a primary consideration when you're choosing the platform for sequencing your project. Element may have some examples where it does come into play. What are you going to get when we deliver VD data sets to you? It's going to look highly similar to Illumina data sets. We provide a basic QC report that'll look basically identical to the Illumina basic QC reports. And you'll have a set of FASTQ files. Some very minor differences. Aviti FASTQ file names have a slightly different format. It's just the sample name and the read number as compared to Illumina sample name formats that include the sample number, lane number, a couple other items. A notable exception is for 10x projects. 10x projects you typically analyze with 10x software, and 10x software expects your FASTQ file names to be named following Illumina style format. So we will deliver Aviti FASTQ files in the Illumina format style for 10x projects. If you open up a FASTQ file off the Aviti instrument, take a look at what it looks like. It's basically identical to Illumina FASTQ file, same format for the sequence IDs. So any software you're using to work with Illumina data sets, you'll be able to use to work with Aviti data sets as well. If you have other questions about some of this data, feel free to talk to me during the break. That's all I'm going to share with you at the moment. And we'll next turn it over to Andrew in the Innovation Lab. Thank you.
Hey everybody, I'm DeGerald Goal. I lead the UMGC's Innovation Lab. And we established the Innovation Lab with these 3 goals in mind. First, to try to help catalyze genomics research here at U of M through research collaborations, and to elevate the UMGC's contribution to the academic discipline of genomics research. So we do a lot of work on optimizing methods, and we wanted to be part of that broader conversation in the field. And then to do this through establishing externally funded research programs. So we wanted this R&D that we're doing to be grant funded, and we've been really successful over recent years in getting grants from a wide variety of funders to help support this research. And then we had the goal of trying to develop methods that would improve the accuracy and reproducibility of genomics data, and to expand the scope and scale of the types of measurements that we can make. And so I'm really excited to introduce Andrew Alegria, who's a grad student in the Department of Mechanical Engineering. We've been collaborating with Andrew and his lab over the past 4 or 5 years. And I think his project really kind of exemplifies all 3 of these goals. So we've managed to get a couple of NIH grants together with Andrew's advisor. And Andrew's going to be telling you today about a new tool that he's developed that I think really gives us some unique capabilities and really allows us to use these next-gen sequencing technologies in new and exciting ways. So please welcome Andrew to GenoFest.
Great. Thanks for that introduction, Daryl. Yeah, so first, today I'll be presenting an automated microinjection for next generation genome editing in multicellular organisms. And so the first thing I'd like to talk about is how next generation sequencing kind of enables these really new types of experiments, such as deep mutational scanning. And so what this figure here is showing is an example of a deep mutational scanning experiment. So deep mutational scanning is a high throughput functional assay that measures the effect of every genetic change at every site in a protein. So for example, mutations are introduced to each site in a protein, and then using next generation sequencing technologies, we're able to count variants and determine how enriched or depleted they are. And so currently this has been done in single cellular organisms. but it hasn't been able to been done in multicellular organisms such as Drosophila, because the amount of mutations that you would have to introduce to run this demutational scanning experiment in an enhancer region, for example, in Drosophila, would be on the scale of 100. And in order to introduce those mutations, you'd have to do thousands and thousands of microinjections. But manual microinjection doesn't really allow for that kind of process to happen because of the way that it's performed. And so just to give some more background as to what manual microinjection is, this is a video of manual microinjection of Drosophila embryos on a cover slip. And so the way that this process works is you have flies in a fly cage, and the flies lay their embryos onto an agar plate. And then once they've done this for about 30 minutes or so, you're able to collect these embryos, dechorionate them so you can remove their shell and prepare them for manual microinjection. And then one by one, line up all of these embryos onto a cover slip, and then use the manual microinjection manipulator to insert the needle into the embryo, and then do your microinjections. So this procedure is very tedious, and only highly skilled technicians can do these experiments. And even at that, the scale that you would need to run large scale experiments in terms of thousands of microinjections wouldn't really be possible. And so it was developed in the 1980s by Rubin and Spradling, and it's a very powerful technique because it allows you to modify the genomes of certain model organisms. And some more common applications that microinjection is relevant to is one, in vitro fertilization. Also, it's used to genetically modify mosquitoes by microinjecting the mosquitoes to potentially eliminate diseases such as malaria. And also for genetically modifying fruit flies and zebrafish embryos for drug discovery and basic research, and just microinjecting for other model organisms as well. But what we wanted to do was try and reimagine microinjection so that we can eliminate all of the tedious steps that go along with manual microinjection, such as the dechorionation and lining up of the embryos on a cover slip, and instead kind of just do the automated microinjection on the embryos that are laid by the flies on the agar plate, and then just be done with the experiment there so you can be able to increase throughput. So the first thing that we did was turn towards machine learning. And so what we did was take thousands of images using a DSLR camera so that we could get a macro scale image of all of the embryos on the Petri dish. And then from these images, we annotated where all the embryos were. We did this for Drosophila and zebrafish embryos, but you can do it for really any model organism that's of similar scale. Once we acquired enough data, we were able to train a model and successfully detect our embryos. So that's what's being shown here. We can successfully detect the embryos with the true positives, and we get very few false positives and false negatives. And so once we were able to do this at macro scale, we wanted to kind of image the embryos and use our machine learning model to figure out where we can inject on these embryos, and also detect the pipette tip at high resolution. So using two 2x inclined microscopes, we were able to visualize the embryos in 3D space, acquire thousands of images again, annotate where we want to inject on the embryo. So it's the posterior for the Drosophila embryo, and then the yolk for the zebrafish embryo, and then also annotate the pipette tip. Then send this data to a machine learning model, train the model, and then successfully detect the pipette tip along with the injection point of the embryo. And so now that we were able to kind of have those two machine learning models working, we wanted to implement this into an automated microinjection workflow so that we can essentially put the dish with all the embryos on the Petri dish, put it into a robot, and then just hit run and automatically do all of the microinjections for that given Petri dish. And so what I'm going to show here is a video of the microinjection procedure working, and you can kind of follow along with the steps on the right. And so what we do is we first image the dish with the DSLR camera. We send that image to our machine learning model, detect where all the embryos are, find an optimized injection path. And then for that first embryo detected, we detect our injection point, insert the needle into the embryo, and then eject our solution using a pressure regulator. And then we can watch another one again. So we find our injection point, hover over it, and then inject our solution. So now that we were able to do automated microinjections, we wanted to see if we could do similar experiments that manual microinjection has allowed. And so some of these are, transgenesis experiments or mutagenesis experiments, and we wanted to do this in Drosophila in zebrafish embryos. And so what we did was successful piggyback transgenesis, 5C31 mediated transgenesis, and CRISPR mutagenesis. And with these experiments, we were able to achieve similar injection efficiencies to that of manual microinjection. And then also we did this for zebrafish, and we were able to get successful GFP transgenesis and RFP transgenesis, and again, maintain similar transformation efficiencies to that of manual microinjection methods. And so the next thing we wanted to do was see if this robot can really allow for the large scale types of experiments that manual microinjection doesn't allow you to do. And so this brings us back to the mutational scanning aspect of the talks. And what we wanted to do is run these mutational scanning experiments for a developmental enhancer region in the fruit fly. And that region that we're trying to saturate is the apterous enhancer region. And so the apterous enhancer region is important for wing development in fruit flies, and mutations to this region will affect how the wings develop in the fruit fly. And so some prior work has already been done to identify conserved regions in the apterous enhancer that affect wing development. And so, for example, one of those regions is C2. So work has been done to figure out if you remove this C2 region, you're able to create flies that have no wings at all. So they're called apterous no flies. Apterous no mutants. And then the other region that's important is the removal of C5. So if you remove the C5 region, you create flies that have these sort of deformed wings, and they're called hypomorphs. But what this work doesn't tell you is where those transcription factor binding sites might be in those regions, because in order to figure out where those transcription factor binding sites are, you need to introduce hundreds of mutations, which again means that you would have to do thousands and thousands of microinjections. So that's where we wanted to use the robot to kind of see if we can do this experiment successfully and do thousands and thousands of microinjections. And so we've attempted this experiment a couple of times, and I'll go through how we did it the first time. And so what we did is we created an array oligosynthesis, PCR'd our amplicons, and then we were able to have our guide RNA pool mix. And with this guide RNA pool mix, we did approximately 10,000 microinjections directly into our germline CRISPR background. And from this, we were able to cross our resulting flies to the apterous enhancer deletion. And then from that, we were able to reveal our phenotypes, score for those flies, and then the mutants that we obtained. We did a PCR of the apterous enhancer region using PacBio sequencers. And so the results were not what we expected, which is why we attempted another time. But basically what we're seeing here are 3 different mutants that we obtained. But the thing is that we did 10,000 microinjections, and we were expecting to see hundreds of mutants. But one of the reasons why we believe that we didn't see the amount of mutants that we wanted, and also had very high lethality, is that the kind of mutations that we were introducing into the apterous enhancer region were quite large. And we believe that happened because we were directly injecting the entire guide RNA pool into the apterous into the embryos. And so as a result, we were getting very large deletions, and we were getting the mutants that we expected in terms of, so we got 2 apterous no mutants and 1 hypomorph, but it caused very high lethality because potential of off-site cutting. And it also didn't give us the fine detailed mapping that we would need to figure out where these transcription factor binding sites are, because the deletions were so large. And so we knew that at this point we needed to go back to the drawing board and figure out a way to introduce these mutations at a very small scale, so we could get the kind of fine detail mapping that we would need to find the transcription factor binding sites, but also do it in a way that isn't very lethal and would allow us to potentially maintain hundreds of mutants. And so what we did first was kind of take a step back from this experiment and try and do an experiment where we microinjected a diverse plasmid library for large-scale genetic barcoding. And so the way that we did this experiment was we microinjected our diverse barcode library into an AppP landing site using 5C31 mediated transgenesis, which we previously validated with the robot. And from this, we were able to establish transgenic fly lines and isolate these individual flies, these individual transgenic flies, to extract their DNA. And then we were able to amplify the barcodes and recover these barcodes using Illumina sequencing. And so for this experiment, we injected approximately 1,700 embryos. We created 410 unique transgenic lines. And on average, we had 3.9 independent insertions per successfully injected embryos. And for even one embryo, we were able to yield around 15 independent barcodes. And so what this experiment allowed us to do was establish these transgenic fly lines by doing just a couple thousand injections. And we wanted to see if we can do this experiment with the apterous enhancer and kind of indirectly increase the amount of mutants that we would need, that we want, so that we can kind of figure out where these transcription factor binding sites are. So we basically combined this experiment with the last experiment that I was talking about. And so what we did was, similarly, do our array oligosynthesis, get our amplicons, and then get our plasmid pool. And then we microinjected this plasmid pool into our embryos. But the difference here is that, again, we used 5C31 mediated transgenesis to inject this into an APP landing site and establish our transgenic lines. And then we crossed it to our germline CRISPR background, which is, what we originally injected in our first attempt. So we crossed it to that germline CRISPR background. Then we were able to identify the transgenic flies and cross them to the apterous enhancer deletion. And then we scored for these wing phenotypes and were able to amplify and sequence them using Illumina sequencing or next generation sequencing. And so our preliminary results are as follows. So these are just some of the sites where the guide RNAs made their cuts and the kind of mutants that they produce. So you can see the apterous null and the hypermorph. And so currently with this experiment, we've injected around 8,000 embryos and scored them for 3,000 injected embryos. We produced 73 transgenic vials, and we've obtained 17 mutants. So this is, obviously much more than the 3 mutants that we, obtained from just doing 10,000 microinjections. And our efficiencies have improved to, 22%. And so we believe that if we keep running this experiment, we'll be able to saturate the apterous enhancer region to the level that we'll see the transcription factor binding sites and kind of show how we can use this robot at large scale to enable sort of new science. And just to conclude, I just like to kind of compare the robot to sort of the next generation sequencing tools that companies like Illumina and others have to offer. So this is a MySeq. And, obviously it's allowed a bottleneck to be cleared to enable new science and new research. And that's kind of what we'd like to do with this robot. And so we're currently trying to commercialize it through our startup, Objective Biotechnology. And we have the robot in a couple labs. And what we'd like to do is, again, eliminate the bottleneck that microinjection has created and basically allow researchers to do large scale experiments. And through that, utilize the capabilities that next generation sequencing has to offer. And so with that, I'd like to acknowledge everybody that's helped me out with this research over the past 5 years. So Suhasa, my PI in the BSBRL group, Ame, who did a lot of the zebrafish work for the robot, Daniel and everybody else in the BSBRL group. And then also everybody in the innovation lab, Daryl, Ben, Jorge, Margaret, Lindsay, Troy, and Victor. And then the funding for this research came from the NIH, and then just like to disclose I'm a founder of the company Objective Biotechnology. And then lastly, there's lab tours going on where I'll be doing live demos of the robot. So if anybody wants to come in and see the robot hopefully working, then feel free.
So thank you, everybody. Good morning. Not only I was at Solexa when I got hired straight out of my PhD, I was supposed to be working on single molecule sequencing. So by the time I interviewed to the time I started, the company had bought Mantea, so working on clustering, and not only that, but then we merged with Link, so we were like completely different company. But I'm glad I made that choice, and it's been the most rewarding 20 years of my life. So for us, it's a really important year. This year is our 25th anniversary, a quarter of a century, enabling customers to unlock the power of the genome. And we all know we know at Illumina, our mission is to improve human health by unlocking the power of the genome. And we had been doing that with this genomic technology that we bring forward, particularly with our sequencing technologies. we have launched sequencers that allow all our researchers in academic, government, and clinical and commercial settings to comprehensively understand the genome and how it translates into health and disease. So what for many of us started at some point a while into a cool technology, now became an actual thing that changed the world, and being part of that, we are all being part of that, is actually pretty rewarding. So for those of you who don't know much about Illumina, we are a leader in DNA sequencing and array-based technologies, headquartered in San Diego, California. We not only do what I consider cool things, so I'm the vice president of R&D in advanced science, so all of the chemistry consumables and library prep products come from my group. But we also try to think about our customer and how our technologies would enable clinicians and researchers to understand the genome, but also tap its full potential. So currently we have around 10,000 employees worldwide, so we have a global footprint. We were founded in 1998. We have more than 9,000 customers worldwide. And last year, at the end of 2022, we installed over 23,000 systems across the world. So when Solexa started and then Illumina acquired us, customer support was done by the R&D scientists, and it's like whoever you got, it's like whatever service you got. I don't think we're there anymore. You all have seen this. Our customer support and our supply chain and infrastructure in operations is world-class. So we could consider ourselves the most reliable, to provide the most reliable genomics infrastructure. And we have invested billions of dollars in supply chain and operations. We have a global operations and supply chain employee base of around 3,000 people worldwide. And we have worked hard to in-source critical components so that we don't put at risk our supply chain, so that when you buy an Illumina product, you know that you will get it. So besides all this infrastructure that is needed to run a successful business and allow you guys to run successful businesses and research, we also try to make sure that we enable you to make an impact. So our performance has been able to do that. We talked quite a lot about quality and performance over the last few months, and I'm gonna give you a sneak peek of some of our recent data. So over 350,000 publications have been put in the world through sequencing technology powered by Illumina sequencing. Our customer satisfaction is pretty high. And we have around 650 people, or more than 650 people, support personnel to help you in any problem that you may have, and we'll support you with global trainings. So as we create our sequencing platforms, and we think about what is that the customers need and what are the things that we have to bring forward, we've created products that expand throughout the output of portfolio, the output of sequencing. So our benchtop sequencers, the tried and proved MySeq, is still out there after 15 years or so. And then our latest sequencer, the NextSeq 1K2K, which you guys have used here in the core, has been pretty remarkable in the way that it has changed benchtop. And of course, our production scale sequencers that with the NovaSeq X series, we launched X Leap Chemistry, and I'm gonna talk a little bit about it in a minute. So NovaSeq X launched earlier this year, and or was it last year? I don't know, it's a blur. Since COVID, I don't think I have track of time anymore. But it provides the most powerful instrument to unlock the genome. With one of those, even though Kenny doesn't want one, but he will want one at some point, you could do 20,000 genomes per year. And XLEAP SBS, which is fueling this beast, allows us to do 2 times speed improvements, 2.5 times the throughput per run, and it's a sustainable system. For those, I mean, you probably have seen the 6,000 boxes. They're big. The NovaSeq X box is like super small. It's the only high throughput system that ships all their reagents at ambient temperature, so without requiring dry ice. And we actually thought quite a lot about environmental impact when we created this, and we made changes specific to our chemistry to address some of those issues. So maintaining quality, reducing waste, and helping improve the impact on climate change. So all of this, and we didn't have to sacrifice in cost either. So with the launch of the 25B flow cell that is coming very, very soon, we will be able to enable a $200 genome with analysis. Remember, this system also has integrated analysis, so it allows you to have the lowest cost possible for a genome out there today. So we can talk about quality quite a bit now, and this is data that we haven't actually put out there publicly yet. But when you look at the specifications for the NovaSeq X, the 10B flow cell is the flow cell that is currently on the field out there. And the specifications say that 85% of the data is above Q30. So the way that Illumina has done Q-scores since Q-scores were invented is in 3 bins, and that's how we put our data. But we have internally the ability to look at our ambient Q-scores. And what we saw is that when you look at the 10B flow cell, 2.41 terabases of the output were above Q40. So a bit over 80% of all the data that we generate on the 10B flow cell is above Q40 as well. And so what, right? So yes, quality scores are important for certain applications, for others not so much. You still are driven by coverage and sampling. But when you put together the Illumina data on the NovaSeq X with our analysis solution in Dragon, what we see is that we have the most accurate variant calling that you can get out there. So there is public data from Element in this case, and we see that when you use the Illumina complete solution on the same sample with Dragon, the number of false positives and false negatives that you get for variant calling is the most accurate out there. So we're still the most reliable and high quality system that you can have for variant calling in the world. So, and I'm gonna go away from our high throughput system and start talking a little bit about the benchtop, our dear and loved NextSeq 1K, 2K. Since we launched this system 1.5 years ago, what we were able to do was provide a flexible and scalable system that has 11 kit configurations right now. So for every output, for every experiment, for every project, there is the right flow cell size and kit size that allows you to achieve that. It has a stream workflow with onboard Dragon. So if you have your own system and you don't have a bioinformatics center to help you, you can get most of the analysis done yourself in there without having to pay for extra analysis. It does have the Illumina quality, not only in sequencing, but also on the rest of the support that we provide. And we didn't just launch this system and that's it. We continuously improve it and try to come up with better consumables and better quality into those. So coming soon in the first half of next year, the XLEAP SBS chemistry will migrate from our flagship production product on the NovaSeq X to the NextSeq 1K, 2K. And that will enable us to unlock the next level of scale, cost, efficiency, and capabilities. So I'm gonna tell you a little bit about the kits that we're gonna be coming on the NextSeq 1K, 2K. And if you have questions later, the sales team is here to talk to you about it. I'm not the best one at that, but I'll try. So the P4 flow cell, which is the one that is coming in Q1 of 2024, will have different kit configurations as well that will allow us to do different types of experiments at different sequencing cycles. So we'll still have the 2x50 cycles or below, the 2x100 and the 2x150 cycles on the P4. We're not launching the 2x300 cycles on the P4 at this time. And that will allow us to do increased batching and increase the scale of the experiments. And you guys saw earlier some of the prices that you can get with some of the other systems out there. With the P4 flow cell, we're happy to say that the price per G will go down to $9 per G. And actually, when you're running experiments like single cell or spatial, where you care more about the number of reads that you get, the price will be between $1 and $1.50 per million reads for that particular flow cell. So now, yes, yet another stair-step change in price that will allow you to do bigger experiments, more powerful, with more data for the same price that you had before. So at the same time as we launched the P4 flow cell, we're bringing the XLEAP SBS chemistry to some of our other products. Other flow cells. So the P1 and the P2 flow cell with a 600 cycle kit. will enable us to do metagenomics, immune repertoire, or small whole genome sequencing projects as well. And XLEAP SBS and the quality that it brings with it enables us to do some of these longer read experiments with much better accuracy. We know that cost and infrastructure for running some of these instruments is difficult. So in the NextSeq 1K2K is the only benchtop sequencer that has integrated onboard analysis at no extra cost. So it just comes with the instrument. And that allows you to run 16 times faster than any of the open source methods out there. It saves on storage cost. It allows for better data compression, so you can move data easier. And overall, when you compare it to other methods, it will save a lab that runs this system over $100,000 over 5 years. So like I said, we're bringing XLEAP SBS chemistry to the other flow cells, so the P1, P2, and P3 kits, with improved runtime and performance. The P4 flow cell, which I don't know how much you know about it, but it will allow you to do 500 G of data and 1.7 billion reads per run. So it's a really powerful tool. And not only that, when you compare, so we all love the NextSeq 1K2K. The data quality is great, it's awesome. But with XLEAP SBS, it becomes even better. So almost a 50% reduction in error rate from the old chemistry to the new chemistry. And this is particularly important when you're looking for those long read applications. So in blue on that chart, I have the current SBS chemistry running on the NextSeq 1K2K, but when you compare it with the XLEAP SBS chemistry, we see that the error rates, particularly at the latter cycles of the runs, become much lower. So around 1% error rate for the end of the run for a 600 cycle kit, it is pretty remarkable. And we think that it will allow for those long libraries to actually obtain much better quality. So I thought I could spend a little bit of time talking about multiomics and how we would use NextSeq 1K2K in some of those experiments. I don't think I need to educate people in this room about what multiomics means, but just to make sure we're all on the same page. NGS has enabled multiomics for the longest time, and it will continue to do so. And when you look at multiomics, you can look at it at different levels. You can look at it at the bulk level, where you just mush up your tissue or whatever sample you have and look at it all together. And you can look for any ohm at the bulk, but you can't get resolution about which specific cells actually are behaving one way or another, or where that transcript came from. Single cell enabled us to move one step further and understand these cells are having this differential expression with respect to the rest of them. And lately, with the spatial sequencing and spatialomics, you don't only see which cells are doing it, but you can also see what is the spatial relationship between these cells within a tissue. So we're starting to understand more biology at the system level of what is happening with this cell and how is it affecting its cells nearby. And sequencing has been and will continue to be the tool that continues to power this and continues to power these biology experiments. Biologists should not care what technology goes behind their experiment. They should know that the data that they're getting out of it is the best possible data and they can just trust it. So when we think about that and how sequencing enables all these other multiomics experiments, we need to make sure that Illumina works closely with their partners in other fields, in other segments, so that we can provide you with a seamless solution. So one of the things that we want to do and continue to do is to provide end-to-end solutions moving forward, so that you don't have to get your own building blocks and your Lego pieces to try to figure out how everything fits together. So from tissue preparation and single cell isolation and library prep, we obviously provide the sequencing and analysis tools, but also make sure that our solutions are compatible with data visualization and interpretation tools. So there is really, really important for us. So if we go a bit deeper and talk a little bit about spatial sequencing and how it works. So in general, most products have an array or a slide that has barcodes attached to that slide, most of the time some beads. And those beads have oligos that have a capture region and a barcode that then allows you to reconstitute where that transcript came from in the original tissue. So this analysis is being powered both, you can run it with 10x, you could run it with NanoString, and Illumina powers it equally with both. And we have analysis solutions for it and compatibility with the solutions that 10x and NanoString provide. So when we think about how the NextSeq 1K2K helps this, it provides this flexibility and scalability for a wide variety of experiments. So in this case, we're looking at whole transcriptome atlas experiment with geomics, for example, and with a P1 flow cell that has 100 million reads, you could do one sample around 12 regions of interest, but you can scale up with the different flow cells to increase the size of your experiment and the power of your experiment. With a P4 flow cell that is coming with 1.7 billion reads, you could do 204 regions of interest or 17 samples. So now these experiments the atlas experiments that are being done can be done in one flow cell of an NextSeq 1K2K. So I think that is pretty remarkable. And like I said, XLEAP SBS not only brings better data quality to the system, but it also allowed us to do price reductions with the P4 flow cell. So when you look at the cost savings compare to the P3 flow cell on the current SBS chemistry, or the NovaSeq X 1.5B flow cell, which will be round about the same output as the P4 flow cell, the P4 flow cell now allows you to get NovaSeq X prices on a benchtop sequencer, which I think is also super enabling. So you don't need to be a massive lab that has a NovaSeq X full all the time to run it. You can access some of this pricing and ability to run experiments just by using these benchtop sequencers too. So scalability, customer support, satisfaction, and delight is one of the things that we want to continue to do. We know that for us to continue to unlock these multiomic insights, we need to provide you with comprehensive solutions. We need to partner with our customers to know what you guys need and try to adapt our roadmap and our offerings so that we fulfill those needs, and also work with the partners out there to continue enabling genomics and continue to adopt, continue to make genomics the standard for everything. I do work for Illumina. I am very biased in all my views, but seeing how the world of genomics has changed over the last 20 years has been an incredible journey. Knowing what we can do today and thinking that we could do this 20 years ago, it was like, you could not even imagine it. So I am very proud of where we got and excited to see how the field is changing and how we catalyzed this industry to continue providing better solutions for all the researchers. So, like I said, I am biased to Illumina. We're here to support you every step of the way, from comprehensive support and expansive peer network. So being part of the Illumina community allows you to access all of the people that are actually doing your experiments. Somebody else will have your same question on how to do something. We like to help you connect with others. And also, we continue to do innovative collaborations with other providers, expanding access to NGS, pioneering new applications, funding innovative startups, and doing way more. So we're here to continue moving the field forward, and we want to make sure that we do it with you. So if you have any questions about your NGS experiments, our sales team is here today to help you. That QR code, I think, allows you to access some fancy booking systems, so you can contact them and make an appointment next week or whenever you're available. So Brenda, Logan, and Foley are here somewhere in the room if you have questions, or you can contact me in LinkedIn too, and I can try to help you however I can. So, like I said, looking back on our partnership over the years has been an incredible journey. Seeing how genomics has grown, how accepted and widely used it is, and the many and hundreds of applications that are being created every day has been a pleasure for me. And I know that we're just getting started. At some point, genomics will be the way that we do everything in health, and we will be able to fulfill our mission of improving human health. So any questions you may have, I'm available. Illumina is here for you, and we will continue innovate to serve your needs. So thank you.
Thanks for having us here today. I'm Solomon Hailu. I'm the applications technical specialist, and I'm actually accompanied by Bill, our FAS, and also Scott. Please join us at the booth. We're happy to discuss any projects that you may have. For today, I would like to begin by stating our mission. And basically, we are here to empower the scientific community through innovations, flexibility, and affordability so that we can collectively impact humanity. Since we launched our initial platform last year, we already have placed over 100 instruments, and we have diverse customer types from core labs, genomic centers, clinical, government, and service providers as well. But for today, what I want to talk about is how are we different in terms of our sequencing innovation? And then what does that differentiation mean in terms of going to different application? And if I have time, I will probably show you a sneak peek of where we're headed in the future and how our innovation paths will look like. So just to give you a brief introduction, we have two platforms, the Aviti and the Aviti LT. And the Aviti has about 1 billion read capacity per side, since we have dual independent flow cell capability. That means 2 billion reads per run. And then the Aviti LT has 500 million per side, which means 1 billion per run. And they both have high quality in terms of accuracy. We're talking about Q40 greater than 80%. That is 1 in 10,000 error rate probability. And the price is described. I will shy away from the price because already it has been discussed earlier by Aaron and John also. But then the platform actually provides low duplicate rates, low index hopping. It is compatible with low diversity samples and additional features which I will highlight based on data. In terms of flexibility, we have 3 different flow cell configurations from high, mid, and low. And each of those flow cells come with dual independently addressable lanes. So you can be able to load different projects on different lanes. This will be enabled in Q4. And then also we have different cycle configuration from 150 to 300, 2 by 300 cycle kit. And that allows us to be reaching in terms of different applications. For example, we could do trios, whole genome sequencing. We could be able to do liquid biopsy. We could be able to do exome sequencing. We could be able to do epigenetic application. And particularly in low diversity, that is where we also shine, because typically for low diversity samples like methylation sequencing, for example, you need to have 30% or more phi-X in terms of to diversify your sample. With our platform, basically, you do not need any phi-X, but at least we recommend 2 to 5%. So imagine how much cost saving you get and effective coverage. So there's greater advantage with that. And we also have the loop-seq technology that can do long-read, synthetic long-read. And I'll also highlight what implication it will have for your research. But basically, the flexibility of the platform, also the low cost is already addressed, so I don't have to repeat that again. But what is also unique about Element is the price is guaranteed for the life of the instrument. So there's no price increase every year that you may expect from other vendors. And so let's talk about innovation. So how are we different in terms of our sequencing chemistry? So there are every element of the sequencing workflow we have innovated, from the flow cell surface, from how we amplify DNA, how we sequence, and also the bioinformatic tools we use to call those colonies or clusters. But for today, I'll highlight the top 3. And if you have questions, I'll be more than happy to discuss the other aspects as well. So let's look into the first innovation. So our flow cell surface is one of the unique innovations there. It has a low binding surface, but what is interesting is we use rolling circle amplification. So your linear library gets circularized using an adapter. We attach it to a surface primer, which is on a flow cell. And using polymerase, we actually amplified the original template again and again up to 1,000 copies. And then this long single-stranded DNA then clustered into smaller clusters, which we call colonies, or cluster commonly referred as. So what is unique about this rolling circle is if you have an error in copy 1, it is not reproduced in copy 2. So each time you're copying the original strand. This is different from SBS chemistry that Illumina uses, where you have linear library, you amplify that, create a PCR template, and then those templates gets copied and copied and copied. So if you have an error at the beginning, so you clonally amplify that. So I don't think that is different with the new XLIP chemistry as well. And so this is something differentiating from that aspect. And the key thing is less error rate in terms of the PCR, because we don't use that. And there is less optical duplicates, and there is less index hopping because of the inherent innovative approach that we use for amplification. Then once we have that surface chemistry and amplification, the second innovation is the avidity technology that we use. So basically the avidites are, they have a fluorescent dye at the core, and the flexible arm is connected to an individual nucleotide. And each of those avidites have the same nucleotide at the end of the arms and have different colors for each of those nucleotides associated with them. So we use 4-color chemistry, and each avidite contains the same nucleotide. So what happens, how do they bind? So the avidite bind to the active sites, right? So each of the nucleotides bind to different copies on the polyny, and each of them are in phase. And the interaction of this nucleotide with the DNA and the polymerase, that stability is where we get the first cost reduction benefit, because this is so stable interaction, so you don't need to drive the reaction with more reagents that are expensive. So this allows us to have significantly lower pricing for our platform, up to 70%. So now let me walk you through each of the steps how we do that. So first, we bind the avidites to the polyny, and any unbound avidite will be washed out, and then we take an image. Once we take the image, we remove the avidite, and then we add a natural nucleotide and then a separate polymerase to incorporate that. And we remove the 3' block, and then the cycle continues again. So one thing important to highlight here is the binding and detection is separate from the extension, which is different from SBS chemistry. So this allows us to actually improve any aspect of that, and we're very flexible to innovate. And you will see some of the innovation down the road as well, and I'll highlight some of those differentiators. So at last, I wish the view from my window would look like this. So there is a dark background with polynies that are clearly identifiable. So we have a high signal to noise ratio, so we can pick colonies easily, even at higher clusters. Because of the low background, it allows us to be able to detect with higher accuracy. So now that I talked about the chemistry, how do we make our platform compatible with diverse library preps? So we actually partnered with downstream and upstream partners we have. So we have tested, as mentioned earlier, over 65 different library prep kits, and we continually test others as well. And that allows us to make sure the burden is taken away from you, and make sure the sequencer is compatible with downstream applications as well. So in terms of analysis, you own your data. You can take the analysis wherever you want. And so that option is available for you. We partner with multiple secondary analysis providers as well. So how do we make the library compatible with the platform? So there are 2 ways we do this. First, the Adept and the Elevate workflow. In the Adept workflow, you have the choice to choose any library you want, right? And once you choose that library, no downstream workflow change. And once you have the library, you circularize it and load that into the sequencer to get your FASTQ file. The second option is you choose any of the third-party library prep kit and change the indexing using our long UDI, unique dual indexes. And by doing that, you can load the linear library directly into the sequencer. So that takes a little bit of 10 minutes of hands-on time compared to the AdDev. And we also have a whole genome sequence library kit, which can be compatible with mechanical or enzymatic assays. So you could be able to leverage that and make life easier with the Elevate workflow as well. And for the informatic aspect, so once the data is generated, as I mentioned, you own your data, but we facilitate that using LM Bio Cloud. So this allows you to actually manage your runs, monitor your runs, or manage users as well and instrumentation, and as well as transfer the data to the source that you have. For example, if you have AWS bucket or Google or Azure, so you could be able to transfer your data directly from the sequencer to that personal, individual, or whatever account you have seamlessly using the LM Cloud system. So as I mentioned, you own your data, we don't see it, we just facilitate the transfer for you, and you can have the secondary analysis of your choice. So now let's look into some of the differentiator. I've shown you about the sequencing chemistry, how it is different, and so how can that impact different applications. So I'll highlight some of the differentiating aspect that we see, and then some of the downstream implication in terms of application. So we have uniform GC coverage as shown in blue, that's the Aviti data. And as you can see, you can call SNPs and indels at higher GC content as well. That is unique for us. And in terms of the other differentiator is long inserts. So again, this is unique to Element. We are able to actually, because of the rolling circle, we're flexible into accommodating long inserts. So this is a data that is generated by Andrew from Google Health. Is again, another source that analyze both the data and show us the results. And as shown here on the left right here, that shows the blue is Illumina insert, typical insert. The yellow or brown is Element's typical insert size. And the green is the long inserts from Element. So when we look into different coverage, no matter what you look, the Element data is superior in terms of precision and recall. And particularly the long insert are even much better than our typical standard library insert size. So that has a downstream implication as well. So we looked into areas where there are gaps in short read technology. So we looked at 4 different sites randomly right here shown. And as you can see, the short read inserts are not able to map into this region. But by having the longer insert, now we're able to map to those regions and call those SNPs as well. So in this case, this SNP would have been a false negative, but it's actually, you have the mutation right there. So you could be able to pick those with having just the long insert. I'm not talking about long reads yet, but this is having long insert up to 1000 KB. That has implication in terms of mapping and the quality results that we get. So we looked into duplicate rates consistently. Our data suggests lower duplicate rate compared to our competitors. And in terms of index hopping is almost negligible. So you could assign your barcodes to the right sample properly and accurately. And we looked into homopolymer regions. So all platforms come in fine until the end of the homopolymer, which is right here at 0. And right after the homopolymer, our platform, the Aviti, continues with lower error rate, but competitors have contextual error that happens and it doesn't recover even you go 100 base pair. So there's a homopolymer issue which we do not see. And this has implications, especially if you're looking into microsatellite instability regions, then that becomes impactful. And we are yet to see what downstream implication that may have. And the quality, I don't have to hone on it. We have data that shows we have higher quality in terms of Q40. In fact, we continue, like I showed you, the flexibility in terms of optimizing. Hopefully, down the road, we even see higher quality. Last year, we released our version 1 chemistry at launch. And within a year, we improved that quality significantly, particularly on read 2. And then we are continually driving this forward. And I can't wait what is the next level we're going to be reaching. So in terms of applications, so what does the quality and the other metrics mean at single cell application? Again, we are one of the two 10x compatible partners, and the standard expectation for this application are listed here. And in all metrics, whether you use 10K or 1K, we are exceeding that expectation. Just to highlight some, the valid barcodes are expected to be greater than 90%. We're at 97% right here. If you look into the, for example, reads mapped to the transcriptome, the expectation is greater than 40%, and we're at 75% right here. And if you look into the quality of the bases, the expectation is greater than 75, but our data suggests we're at 98%. So in all the metrics that you see, we are continually exceeding that, and the platform is suitable for single cell application, and you can benefit from the cost advantage right on the bat. And we do have also the 200 genome kind of a deal, and that also can significantly lower the pricing if you have higher throughput. RNA sequencing, run to run, there's greater consistency across platforms. It's also consistent. But however, when our customer in Belgium looked at the data, compared with a reference RNA and used different platform, NextSeq, NovaSeq, Aviti, and then the BGI, and what you can see is consistently the Aviti data offers the higher quality compared to the other platforms. And this may have implications if you're looking into, let's say, isoforms and hypermutations in those isoforms, then the quality would matter. And so we looked into the genome as well. So when we look at genome, you can consistently see that there's, especially on the lower coverage, there is a significant reduction in a false candidate proposed by our platform compared to the competitor. Whether you look into exomes, similar story, lower candidates are proposed in general. And this is also seen for targeted cancer panels or so that we have looked as well. And so our quality, flexibility also has impact. For example, there are 6 families from Mexico that has actually traveled to the United States to do a genetic test for their kids because they have shown different abnormalities, including heart and developmental delays. So the researchers at TGen actually used a 40x coverage for the proband and used the 20x coverage for the parents and be able to identify the causal mutations or the likely genetic cause for about 67% of the cases. And that actually improved their detection from 40% to 67%. So this, you don't have to wait. The trials can come in, take a sample, run it. You don't have to wait for batching. So that's the flexibility, and the cost advantage also is very clear. But I want to also highlight long-read technology. So we do have a synthetic long-read technology called the loop-seq. So you can tie this from your single cell, and then you want to get the isoform or the full length, you can be able to leverage loop-seq for that one. And if you have, let's say, a metagenomic approach, and you're trying to look into 16S, you can use loop-seq to identify the long reads and be able to classify into species level. And if you want to do immune repertoire or phase the HLA region, then you're also able to do this with our synthetic long-read technology that can be run on the Aviti. How does it work? So we have a barcode that we attach at the end of the molecule and copy it. And once you copy it using our proprietary technology, we copy and paste that in cis. And then you fragment this into smaller insert sites, then sequence them, and then reconstitute the original molecule using the barcodes that you introduced. And that application has been used, and we have multiple publications regarding these applications. But as a scientist myself, what is striking and interesting is what can we do next? So does the sequencer have to be a sequencing machine only, or can we do even more than that? So what I want to highlight is our low binding flow cell surface chemistry allows us to actually bind any nucleic acids. So we can leverage that to actually use a targeted enrichment sequencing approach on our flow cell. Or we could also attach proteins and detect different proteins and analyze. Or we can also be able to sort cells or attach tissues. That is the next level that we're thinking. In fact, it's not even a dream. So I showed you the sequencing data, but this is a sneak peek of some of our preliminary data where we use single molecule antigen detection and also cell culture in the platform itself. So I can't wait as a scientist to see what is the next level, and I hope you join us in that journey of innovation. So this is completely a unique technology, and it has different application, and please reach out to myself or Scott or our FASs as well, and we're gonna be happy to discuss any of your questions, and hopefully you see the differentiation. And yeah, we're small, but we're powerful, and I think with a combined effort and collaboration with you guys, we can do innovative work, and thank you for that.
So as I said, I'm with Olink Proteomics. My name is Sun Lim, and I'm the Business Development Manager. I'm actually from Texas. And I have Sarah Ledley here, who actually covers Minnesota as her territory, as my colleague here today. And we'll be reviewing our Olink Proteomics, our company introduction, for those of you who still are not aware of our company, as well as our PEA technology, which stands for Proximity Extension Assay, and our products that we offer currently. So basically, we are a proteomics company, and we are trying to get to the truth of disease by revealing our protein by protein. And currently, our current library of HT is up to about 5,400 proteins. We are a company based in Sweden. It was developed in the University of Uppsala as a part of a group of graduate students and developed this technology in Uppsala. And we are now a global company that's, we have a base in Boston, as well as Asia and APAC and Europe. So this is a very powerful slide. Within last 2 or 3 years, our company has grown tremendously. We have over 800 customers, both pharma and academia, that are currently utilizing our technology. And I really would like to emphasize our peer-reviewed journal article that's about 1,400 currently. And this is a significant, a lot of those journal publications actually came about within the last couple of years. I started with Olink about 1.5 years ago, and at that time, our publication was at 600. So within 1.5 years, we actually more than doubled our publication. And I think that's very powerful testament for our technology and how all the researchers have adopted our Olink technology into their programs and their projects. This is a basic premise of our extension assay. The core of Olink technology, proximity extension assay, is what has enabled us to be so innovative in the biomarker research. PEA employs a dual antibody recognition, which drives incredible specificity in our assays. Coupling with this, with the PCR amplification, enables robust sensitivity. PCR amplification of the hybridized antibody pairs cleverly transform the detection of antigens into unique DNA barcodes, and this is where genomics work come in. Allowing for extremely high assay multiplexing in very small sample volumes, as little as 1 microliters. Experiments are run across all stages, and the benefit for you is that you don't need to change platform when moving from one phase to another, such as discovery all the way to clinical evaluation. And it enables data consistency, and it will save you time and money instead of moving different platforms. So these are our products, our platform being anchored by our PA technology. We have several product lines. Our Olink Explorer, as you have seen, is our premier discovery platform. Olink Target, which is currently run by the Genomics Core. And also Olink Flex and Focus panel. And those are very small customized panel that can work well in clinical setting. And as well as Olink Insight which is our a program that you can look at different biological relevations for proteins. So again, we're looking at one platform that can go from discovery to clinical translations. And this is very unique in the protein space. We have a lot of proteomics platforms that can only do very small amount of proteins, such as mass spec. Well, we can do large amount of proteins or mass spec, but you cannot do multiplexing up to thousands of samples at a time. Or Luminex or ELISA that can only do very few proteins, and they cannot do multiplexing as well. We're looking at thousands of proteins with thousands of samples. It's very unique with Olink. And this is also very interesting for our technology, is the fact that you can use so many different types of sample types. We are validated on serum and plasma, but we have utilized CSF, cell lysates, tissue lysates, anything you can pretty much think of that can be utilized with our technology. So this makes it very diverse and also very flexible for all your research needs. We are continuing to innovate. As you have seen our latest product, Olink Explore HT. We started out in 2020. We launched our first Explore panel of 1,500 proteins. And last year, on 2021, we launched our next generation, which is 3,000 proteins. And now, within 2 years, we have launched 5,400 proteins. And we are continuing to innovate and add additional content into our library. Again, Olink Explore HT, our newest product, really continues to biological insights with proven specificity at any scale, which means we can run thousands of samples looking at 5,400 proteins at once. And this is truly remarkable for our technology, as well as looking at a large population health studies. And also a lot of pharma companies are interested in data as well. So all of our pipeline, our platform, go from discovery to clinical translation in one platform. And this is very important for those of you looking at discovering and all the way to clinical translations and clinical panels. Going from Olink Explore HT panel with 5,400 proteins, all the way down to what we call Olink Focus panel, which is a customized panel that you can design your own panel for clinical use. And we're the only platform that can do this. One of the best things about Olink Explore HT is that we have increased library to 5,400. Our workflow is simplified. Actually, it's pretty much all automated, from pre-PCR instrumentation for automation to genomics and also post-PCR instrumentation. There's a very little hands-on time and high throughput. You can probably put samples, 2,000 samples a week with this particular platform. And again, we have our own software that can do data processing. So why is 5,300 proteins? We actually tested 15,300 assays, and it went through a vigorous process of validation. And out of that, we have 5,300 that's been approved to be in this assay. We are continuing to innovate, and we will be adding additional proteins to our list. But this is a process that we went through the last 2 years developing this panel. And it is very vigorous. And this is actually modeled by FDA validation. So you can be ensured that all of our proteins going through this rigorous process and specific and sensitivity is guaranteed. Again, compared to our Olink Explore 3000 that was launched 2 years ago, you're looking at a significant difference in throughput, as well as data points, and also 11 million data points compared to 1.5 million data points. As well as looking at, 50,000 samples is a lot, but we have just completed UK Biobank of 50,000 samples, and you can imagine with the Olink 3000, that took us about a year. But with HT, you can do that in 12 weeks of 50,000 samples. That is quite remarkable. There is we are very environmentally conscious, as you can imagine. There was a lot of kits packaged, so we have reduced kits, as well as a workflow and cost savings. So we have reduced the number of labor cost, as well as a number of steps to
amount of making sure that all of these workflow is much more seamlessly into a genomics workflow. So how do we do this? We actually provide kits. Our biggest goal is to externalize our technology into different core labs. Obviously, University of Minnesota Genomics Core is one of them that love to get our kits in here and adopt our technology. We also offer services in our Boston and Uppsala labs. So we do both. However, our goal really is to externalize our technology, and then we love to have every single core lab adopt our technology and offer the technology to their researchers. In conclusion, again, this is brand new on the market. There's really nobody like only technology that can do proteins like we do. So we're very proud to offer this, and the fact that we can seamlessly integrate into your genomics workflow or proteomics. So it's called proteogenomics now, combined together. And it's very easy to adapt, and the power of data of protein is remarkable.
Hi, everybody. My name is Brenda DeGerald. So I'm an array technology specialist, so we'll kind of shift gears a little bit here. Very honored to be here. I've been with Illumina for about 15 years, my first time in Minnesota. For any of you baseball fans, congratulations on Tuesday. Just broke a major losing streak. I don't know a ton about baseball, but I know that it's deep rooted in the superstitious fields, and I know I arrived on Tuesday, so I think it might be important for me to come back next year just in case. There's so many incredible things happening in the methylation space. Just to in case that question's out there, Illumina is very dedicated to continuing to develop and innovate in this space. Our platform really specializes in genotyping methods and methylation methods. So due to the limited time, I'm going to really focus on methylation. This space is evolving very rapidly. And I've just picked a couple of key points I hope you'll find interesting as you kind of think about more thought-provoking experiments you might have yourself in the next couple of years. So kicking right into it, I'm going to do a quick overview of methylation, why it's important and why it's coming up more and more in conversations around multiomics experiments. I've kind of cherry-picked a few example papers that are very recent in the publication reviews. They really, I feel, reflect some of the emerging areas that methylation is starting to have a bigger impact and really showing to have promise in the future of precision health. And then I have just a quick glimpse into a next generation array that Illumina has been working on for quite some time. I'm very excited that University of Minnesota will be one of the first people to bring this on. I got a tour of their lab. I think it's really exciting to see what's going to be possible here in the next couple of years. So I hope you'll keep that in mind. So an overview of methylation. I've seen methylation described in a lot of different ways. People that have never worked with methylation before, it can be a little bit intimidating in terms of how you work with this type of data. So to give you a really big picture sort of analogy, one that resonates well with me, I hope it resonates with you, is that the initial thing we have to do is capture the genetics, right? So when we take a look at a house as an analogy, the genetics really reflect the blueprint. Genetics is the blueprint of your DNA. It's the first thing that makes sense to look into, say, when, hopefully when you're born. That would be a great time to get the essential blueprint of that home. Some homes the blueprint and the original engineering build plan might have had mutations. Maybe the engineer put the wrong type of roof on the house, and that's going to present problems later. So some of the data we can get out of that initial blueprint might be polygenic risk scores. So we can start to see at any point in time in the individual's life, the earlier the better, what type of risks they might be more prone to realizing or experiencing later in their life. But what's kind of becoming more interesting is what's the current state of that biological system. And this, I think we really see a future in which you go to your doctor and you can actually get the current status of your biology. And I really attributed that to, if you were to buy a house, you're not really looking at the blueprint anymore, you're really looking at the home inspection report. And so that current system may have, if you were a house in Florida, you may have experienced certain, hurricanes, or in Phoenix, you've got a lot of heat exposure. So depending on where you live, the exposures you've had, and there's so many different areas, right? Have you been a smoker? Have you been exercising? Have you been on chemotherapies as a child? There's so many different factors. So methylation really tells a story of what happened to you in the past, and it takes into consideration as well the genetics. What were you predisposed to, and sort of how are you tracking toward that original risk profile? So let's kind of keep the ball rolling on epigenetics. It's becoming more and more interesting as we relate genotype to phenotype. We really get a better understanding of the influence of the environment. The environment really has a major influence on whether or not those genetic risk factors ever come into play or not. So it's important that we start to look at that. It's not just inside the biological system, it's the factors that are outside contributing. And we heard a presentation from Olink. It's becoming more and more obvious that when we do multiomics, it's methylation, it's metabolomics, it's proteomics. All of these different factors are playing an important story. So the history of EWAS, and it reminds me very much, it's not too unfamiliar from the history of GWAS. So while GWAS was really focused on associating SNPs to disease, we've come a long way. We've understood more complex biology. SNPs are not necessarily causative, but they are informative. We've also come through sort of a similar history and trajectory through epigenome-wide association studies, or EWAS. Illumina developed back in 2010 one of the largest EWAS tools that's quite prevalent. If you look through any data bank in EWAS history, you'll see a lot of the publications, I think over 90% of them have really come from these epigenome-wide arrays. We have advanced, just like we did in GWAS, the coverage that we can include on these arrays so you can get more and more informative information. We just recently launched the new version of EPIC, which has been around since 2015. We've kind of boosted the amount of content, we've removed some less informative content, and we've been able to take advantage of discovery work that's been done on a subset of sequencing data and continue to empower the discovery power of the array. So when we talk to scientists that are looking at methylation data, of course, more data is always better. Sequencing is still just not really practical in terms of economics, scale, and even digesting this type of data set. So Illumina is going to continue to provide, and institutions like the University of Minnesota are going to continue to be the workhorse for processing this type of data. So yes, we are still doing discovery work on arrays for methylation for the foreseeable future. The cost, data quality, consistency, and analysis are some major contributing factors to that. So now I'd like to kind of just transition into some emerging applications and some interesting new discoveries that have been made. And when I look at these papers, and when we share these papers that I'll be presenting are definitely in a lot of circulation right now because they're triggering conversation, ideas. How could I apply these findings to my work? The theme that I see, and I just wanted to call it out here, is we're really getting closer to precision with methylation. And you'll see that it's happening upstream and predictability of future clinical outcomes, but it's also telling a really good story of the current condition of that cohort, of that individual. And I think because of the work of institutions that happen here, we're going to get closer to this becoming a reality in our lives as patients. So I think that's, personally, I find that very inspiring. And I hope that we're providing the right tools and getting your feedback so that we can continue to do so we get there faster. So this paper has been a milestone paper, actually. This was presented some authors that came out of UCLA. This paper was just published in August of 2022, so just about a year ago. I thought I'd give a quick grounding of what this did. This paper sort of coined the term MRSs, or methylation risk scores. So at UCLA, they have a biobank of about 50,000 individuals. They're highly multi-ethnic, coming out of Southern California. They have blood samples. And so there's kind of two things that are really important here. They have They have blood, they have diversity, they have EHR data. So when it comes to methylation data, or again, getting that inspection report from that home, you have to be able to say, what does that mean? And what can we do about it? And so that's where authors such as this are getting us closer to those questions. So what they did is UCLA, they did a PRS many years ago on a genotyping. You can do PRS with whole genome sequencing. Some people do some exome sequencing or genotyping. They chose genotyping. They developed some PRSs. So then they decided to kind of do a follow-up on a subset of their biobank and overlay methylation data to kind of see how methylation changes the predictability of the clinical outcomes of those individuals that were in their biobank. The reason why they were able to do that is because they did have EHR data. EHR data is very important to have. Clinical phenotypic data is important to have, because what the methylation data can do in combination with AI or machine learning or sophisticated algorithms, you start to find signatures in the data. You have to correlate those signatures back to phenotypes. And so having that data is really, really rich. And so we're constantly talking to individuals that have interesting cohorts, and it might make sense based on the information you have of those cohorts to not just do genotyping, not just do sequencing, but to really start layering on methylation. And a lot of individuals are starting to do those both at the same time. So what these authors found is that, in fact, the methylation risk scores were significantly more predictable than the polygenic risk scores. The polygenic risk scores in the genotyping or sequencing was important. It lays the groundwork. But in terms of predictability, we're starting to see we get a lot more information. You get biomodal type of layered, you can layer and layer all kinds of information from the clinical phenotypes and present a story with some sophisticated AI or machine learning algorithms. We're seeing that happen now. So the next step is, and why methylation is also really, really interesting, is because it has the potential to be reversed. And so can you correct the disease? Can you improve the condition? So another paper I'm going to mention, this is again with the theme of precision. The author here, Dr. Charlotte Ling out of the Lung University, she decided to focus on diabetes type 2. Diabetes type 2 is one of the highest rated disease conditions in the United States, a good one to focus on. To date, if you go to the doctor and you get diagnosed with diabetes, they tell you have diabetes type 1 or diabetes type 2. What this researcher did is she took a look at diabetes type 2 individuals, layered on methylation data. You get really precision, you get a lot of precision around your phenotypic data. You layer on AI, so similar to what UCLA did. She actually found that she could subclassify diabetes type 2 into 4 different groups. Those groups were individuals who were insulin deficient, insulin resistant, obesity-related diabetes, or age-related diabetes. It turns out that not all individuals, individuals within those different groups should not necessarily have the same clinical treatment plan. So it's a really interesting step in the right direction. I found that to be a bit inspiring myself. Aging is something that is talked about all the time. The aging clocks were actually developed by Dr. Steve Horvath quite a long time ago now in the original Infinium methylation 27K. He has evolved that to the 450K, the EPIC array. But now there's all kinds of clocks that are out there. We have chronological clocks that can tell you how old you are, confirm that. That's actually starting to get more interesting in some consumer applications, canine, things like that. You know, can you tell the age of your dog, for example. But what's more interesting in human research is the biological clock and saying, you know, are you aging at an accelerated rate? Are you aging at a decelerated rate when you compare that to your chronological age? But then recently, there's been a step further is to split these into different health systems. So you might, on average, your biological clock might say you're 34, but if you start looking at your individual health systems at the organ level, some organs may be aging at a decelerated rate, 32 in this example, or in this case, 54, and that kind of really can lean or have the clinicians start to hone in on where the next level of omics should happen, where the clinician might in the future start to be focused. So yeah, getting, again, more precision. This is the first application that was ever presented into the clinical world. It's now become a routine level test, which going back to a statement that Cande said, could you imagine this ever happened 10 years ago? I just couldn't imagine this was going to happen less than 10 years ago, that the Infinium methylation epic arrays, which were largely rooted in EWAS studies, are now in the clinic. And the reason for that being is because you can take, instead of looking at histological review, looking at cancer tissue under a microscope and having a neuropathologist make a decision and classification of that tissue type, you can layer on molecular data, and now you've got a very accurate readout of what that type, that classification of the disease is, or even the subclassification. And now there's been new classifications that the individual eye could not, of course, pick up on that have been added to the WHO. So while this is a clinical example, it's a common theme of applying molecular signatures for methylation, layering on some AI, and sort of starting to uncover a lot more information about your cohort. This is the last example I wanted to show. This example is, this paper is really new, actually. I think this paper came out in July or August of this year. There were some people at Illumina that were speculating that this might be possible. We were really excited to see this, this publication. I'm expecting that we're going to see a lot more of this in the future. So what this set of individuals did is they leveraged the immune system's response to disease, in this case, breast cancer being the disease. Instead of looking for the cancerous cells, they were watching the immune system, how's the immune system reacting. And so what they saw is that they were actually able to use peripheral blood mononuclear cells in this case. So unlike a lot of other novel sequencing methods that are looking for circulating tumor DNA or cell-free DNA, they're actually looking at what's really easy to find, which are PBMCs. And what the PBMCs are doing is they're telling a story of what happened, how the immune system is responding. And it turns out the immune system is quite active in the early stages of cancer, pre-cancerous stages. And with incredible accuracy, these authors were able to reliably detect early stage cancer at the even pre-cancerous levels. And they ended up validating their data with targeted sequencing, and they ended up finally developing a test that actually only leveraged, I think, just 4 or 5 of the CPG sites to do a qPCR test that could then be used in the diagnostic industry. So really, really cool stuff. All of this to say that this has led Illumina into a new development plan. So while EPIC is going to be the workhorse of research, we are now moving into an era of launching a new type of array. We're going to call this the Infinium EX chemistry. This is going to be a much higher throughput chip. Just so, you know, as a reflection of the arrays we have today on market, the one on the upper right, EPIC V2, is our current, you know, most modern EWAS type of discovery array. We do have a mouse array that's really interesting as well. Please know that that's available and also through the university here. And we have the ability to customize methylation. If you, for example, found that 2,000 CPG sites out of 920,000 were really important and you wanted to do high-level screening, you can do that through a custom array, and the core here is very well equipped to do that. But now what we're looking at is actually developing this next generation array. We're going to call this array the methylation screening array. This array is coming out in Q1 of next year. It is a much smaller subset of contents. We're looking at about 250,000 CPG sites, but they're very powerful CPG sites that were selected. We had some incredible researchers that kind of mined through the EPIC array that has known associations. And we decided to focus on common diseases. So we removed a lot of the enhancer regions that have to do with oncology research. We focused on common disease variants. We looked at content that would have environmental exposures, which are obviously important for getting a readout of that current home inspection report when you go to your doctor in the future, hopefully. Cellular deconvolution is becoming really, really powerful for multiomics studies. So those types of markers were pulled from the EPIC array and put onto MSA. MSA is about half of the content is going to be pulled out of the current EPIC array. But what our collaborators did is they also mined all of the sequencing studies that have been published to date. And we have about half of the content of this new MSA on this chip. And this is really going to be interesting for cell type specific markers, intermediate methylation. We have hydroxymethylation or 5-HMC regions, and then some cis regulatory elements. We can talk about this certainly more offline. But the idea here is to take more known associations and empower larger cohorts, biobanks, lower cost, higher types of studies. So we can get more of those MRSs developed, for example. So this is the new chip. It's actually going to be 48 samples on one chip. From a scalability standpoint, leveraging new automation, it is definitely going to be the next, I think, workhorse in sort of more translational studies and validation studies. And yeah, we're really excited to have the new automation setup all installed at the new laboratory that Kenny showed us is coming in. Thank you so much for your time today. I did want to just kind of end with a podcast. If you'd like to kind of check it out. These are all science-focused podcasts, all things epigenetics. There's so many areas this type of chemistry and this type of molecular assay is going to impact. And so you can learn a lot from this podcast. They've got some pretty cool scientists speaking there. But yeah, thank you so much for your time, and looking forward to working with you guys.